12,800 years ago, just as the world seemed to be escaping the grip of the Ice Age, something terrifying happened. The warming stopped. The cold came back. In some places, it may have happened within a single human lifetime. Forests stalled, lakes changed, animals shifted, and entire human worlds were forced to adapt to a planet that suddenly turned harsh again. Scientists call it the Younger Dryas, and even now, they still argue over what caused it. Before we go deeper into this ancient mystery, take a moment to like the video and subscribe if this is the kind of history and mystery you enjoy. The cold does not creep in slowly. It does not announce itself with a long and dignified warning, the way people often imagine great changes in the natural world. It comes like a reversal written into the bones of the earth itself. One generation sees the grip of the Ice Age loosening. Rivers begin to run harder with meltwater. Valleys open. Forests edge north. Animals follow new grazing lands. Human groups move into spaces that had once been hard, white, and nearly unlivable. Then, with astonishing speed, the world lurches backward, the thaw falters, the air sharpens, winters lengthen. In places that had begun to soften, cold returns with a force that feels almost impossible. Around 12,800 years ago, just as the planet seems to be climbing out of one frozen age, Earth suddenly slips back toward glacial conditions. For more than 1,000 years, much of the northern hemisphere is thrown into a strange and severe climatic relapse. Scientists call it the Younger Dryas. Even now, after decades of study, they still argue over what exactly caused it. To stand inside that moment, even in imagination, is to feel how fragile any familiar world really is. A landscape that had seemed to promise release begins closing again. Tundra spreads where brush and sparse woodland had started to advance. Lakes change. Winds shift. Dust moves differently across the land. In the North Atlantic region, temperatures plunge with a speed that remains one of the most unsettling facts in paleoclimate research. Ice cores taken from Greenland suggest that some of the change happens not over ages, but over decades, perhaps even faster in local terms. The evidence remains incomplete, and scientists are careful about how precisely they describe the timing, but the broad truth is hard to escape. This is not the leisurely pulse of a stable planet. This is abrupt climate change on a scale large enough to reorder ecosystems, migration routes, and human possibilities. Before we go deeper, take a moment to like the video and subscribe, if this is the kind of history and mystery you enjoy. The name Younger Dryas sounds almost gentle, as though it belongs to a flower pressed into paper. In a way, it does. The term comes from Dryas octopetala, an Arctic alpine plant whose pollen appears in sediments from this cold interval. Where that pollen shows up in abundance, it signals the return of harsh, near-glacial conditions. A delicate flower gives its name to a planetary shock. There is something fitting in that. So much of deep history survives not in monuments or inscriptions, but in tiny residues, pollen grains, trapped bubbles in ice, microscopic shells on the ocean floor, layers of mud laid down year after year in lakes no human being alive has ever seen in their original form. Vast drama leaves very small witnesses. What makes the Younger Dryas so compelling is not only its severity, but its timing. It arrives at the threshold of a new world. The great ice sheets of the last glaciation are already retreating. Sea levels are rising. The giant frozen architecture that had shaped northern landscapes for thousands of years is weakening. Across Eurasia and the Americas, animals and people are responding to this transformation in real time, though of course they do not know it as transformation. They only know routes, seasons, prey, plants, winds, dangers, and opportunities. They knew where the ground is firm, where the herds pass, where fresh water holds late into the dry months, where wood can still be found, where the cold kills quickly after sunset. Then the rules begin changing again. For the people living through it, there is no concept of a climate event with a name that will survive into scientific literature. There is only the returning bite of winter, the rearrangement of familiar ecologies, the subtle failure of old expectations. A marsh that once drew birds dries differently. A stand of useful plants comes in late or not at all. Migratory animals alter their timing. Fish runs become less predictable. Snow cover lingers. The distance between safe camps and reliable food grows more dangerous. In some regions, the change may be felt first in seasonality rather than annual averages, colder winters, shorter growing seasons, sharper swings, wetter years in one place and deepening dryness in another. No single explanation fully accounts for how every region experiences it, because the Younger Dryas is not a uniform blanket thrown evenly across the globe. It is a disturbance in a connected planet, and connected planets produce uneven consequences. That unevenness is part of the mystery. The Younger Dryas is often described as a sudden return to Ice Age conditions, and in broad terms that is true, especially around the North Atlantic. But Earth is never simple enough to freeze in the same way everywhere at once. Some regions become colder, others become drier. Some may experience shifts in storm tracks or rainfall more strongly than shifts in raw temperature. In the Southern Hemisphere, the signals are more complex and do not mirror the North neatly. Scholars still debate how globally synchronous the event really is in all its details, and how best to compare records from distant regions using evidence that is precise in some places and frustratingly blurred in others. Even so, the overall picture remains striking. A major climatic reversal interrupts the warming world and holds it in suspension for roughly 1,200 years. There is something eerie about that number. 12 centuries is longer than many kingdoms last. It is longer than the lifespan of empires people tend to think of as ancient. It is long enough for oral traditions to distort beyond recognition, for migration patterns to reset, for species already under pressure to slide closer to disappearance, for entire cultural worlds to adapt to a reality their ancestors might have believed temporary when it began. Yet in geological terms, it is also shockingly brief. That contrast sits at the heart of the Younger Dryas. For human beings, it is an age. For the Earth system, it is a violent hesitation. And it happens in a planet already full of tension. The ice sheets over North America and Northern Europe are not static leftovers from a finished age. They are active forces still shedding enormous volumes of meltwater. Proglacial lakes spread along their margins, vast bodies of cold, fresh water contained by unstable barriers of ice, sediment, and fractured terrain. Ocean circulation is sensitive to salinity and temperature. Atmosphere, sea ice, winds, and sunlight interact in ways that can reinforce change once it begins. The conditions for instability are already present. The real question is which trigger matters most, and whether one trigger is even enough. This is where the story begins to acquire the shape of a true scientific mystery. There are clues everywhere, but they do not all point cleanly in one direction. Greenland ice preserves annual layers fine enough to reveal astonishing detail about past temperatures and atmospheric composition. Lake sediments carry pollen, charcoal, and chemical traces that record changes in vegetation, fire, and erosion. Ocean cores preserve the remains of tiny organisms whose abundance shifts with temperature and currents. Cave formations grow in ways that reflect changing rainfall, ancient shorelines, flood deposits, and glacial features hint at enormous rearrangements of water and ice. Each archive tells part of the story. None tells all of it. Scientists piece them together like a shattered map from different centuries, drawn in different languages, each accurate in its own limited frame. The result is a picture that is both clearer and stranger the more closely it is studied. On one level, the Younger Dryas is a known event, firmly established, visible in multiple paleoclimate records, impossible to dismiss. On another level, it remains unresolved in the way the most interesting problems often do. Was the main driver a sudden pulse of fresh water into the North Atlantic, disrupting the Atlantic meridional overturning circulation and weakening the northward transport of heat? That is the leading explanation, and much evidence supports some version of it. But the details are contested. Which lake or ice margin released the water? When exactly in what volume? Over what route did the circulation simply weaken or reorganize more dramatically? And if fresh water is the answer, why do some records still refuse to align as neatly as researchers would like? The evidence is powerful, but not perfectly obedient. Then there is the other explanation, the one that reaches more easily into public imagination because it carries the violence of a single cosmic event. According to the controversial impact hypothesis, a comet, or fragments of one strike Earth or explode in the atmosphere, triggering fires, atmospheric dust, ecological disruption, and perhaps even contributing to the onset of Younger Dryas conditions. It is a dramatic idea, and for that reason alone it often travels farther than more cautious models of ocean circulation and meltwater forcing. But mainstream acceptance remains limited. Many specialists argue that the supporting evidence is inconsistent, misinterpreted, or insufficient. Some reported markers have proved difficult to reproduce across sites. Others remain disputed. The theory persists because the evidence is not simple enough to make it vanish entirely, but it has not convinced most researchers as a full explanation. That tension between public fascination and scientific caution is itself part of the Younger Dryas story. What makes the episode feel so modern, despite its age, is that it violates a comforting assumption. People like to imagine planetary change as something too large to move quickly, something buffered by scale, slow enough to remain theoretical within a human lifetime. The Younger Dryas suggest otherwise. It shows that under the right conditions, climate systems can cross thresholds and reorganize far faster than intuition prefers. The world can hover near one state, shift into another, and remain there long enough to become normal to those born inside it. That is not speculation. That is the lesson preserved in ice and mud. And yet this is not a tale of pure catastrophe in the simplest sense. Cold returns, but life does not stop. Humans do not disappear. Animals do not vanish all at once. Landscapes do not become uniform wastelands. Instead, the world becomes more difficult, more unstable, more regionally unpredictable. Some places suffer sharp contraction. Some communities adapt. Some species survive the pressure for centuries before finally falling out of the record. Others find temporary refuge. The Younger Dryas is not only about collapse, it is about strain, resilience, improvisation, and the dangerous unpredictability of transitional worlds. That matters because it places the event not at the end of a story, but in the middle of one. This is the threshold between the Pleistocene and the Holocene, between the old world of mammoths and massive ice sheets and the warmer, more stable interval in which agriculture, cities, estates, and written history will eventually emerge. The Younger Dryas interrupts that transition like a hand closing over a doorway. It delays the new world without preventing it. It reminds us that the climate stability on which civilization later depends is not the default condition of Earth, but a fragile arrangement that must first arrive and then hold. So the mystery begins there. In a warming world that suddenly stumbles, the glaciers have not fully gone. The future has not yet settled. Human societies are still small, mobile, and exposed to every shift in water, wind, and season. Great animals still move across northern plains and cold grasslands, though some are already living close to the edge. Meltwater lakes wait behind unstable barriers. Ocean currents carry heat through a system sensitive to disruption. Somewhere inside that volatile mixture, something happens, or several things happen together. The planet cools, the thaw retreats, a near-forgotten flower leaves its pollen in the mud, and thousands of years later, scientists still stand over cores of ice and sediment, trying to explain how a world that seemed to be escaping one frozen age suddenly fell back into another. Before the cold returns, the world is already in motion. Ice has ruled the northern hemisphere for so long that it is easy to imagine its retreat as a single clean event, a simple ending after a long domination. But the end of an ice age is rarely clean. It is a drawn-out unwinding, full of pauses, surges, collapses, and local reversals. Vast glaciers do not vanish like snow in spring. They crack, slump, melt from below, carve into lakes and seas, and leave behind whole landscapes still stamped with their weight. Around 14,700 years ago, well before the Younger Dryas begins, the planet enters a warmer phase often called the Burling Alarud interstadial. Temperatures rise, in some places with striking speed. The great freeze loosens. The old white boundaries begin to pull back. Rivers fed by meltwater run wild across exposed ground. New lakes form in glacial hollows. Fresh coastlines appear where water and land renegotiate their edges. For plants, animals, and humans, this is not merely a change in weather. It is the opening of a new map. Northern Europe begins changing first in ways that are both dramatic and easy to overlook. Tundra that had dominated under the full glacial regime starts giving way, in some regions, to shrubland and then sparse woodland. Birch and pine advance where climate and soils allow. The ground is still young, often thin, unstable, and scarred by frost action, but it is no longer locked in the same severe pattern. Wetlands spread in low areas. Summer productivity rises. Insects flourish in warming months, and with them come birds in greater numbers. Reindeer still move across large territories, but the ecological mosaic around them becomes more varied. In places once defined by relentless cold and open ground, there is now patchiness, cover, and seasonal richness. The evidence survives in pollen grains, beetle remains, and plant macrofossils small enough to fit in a hand. Yet together they describe a continent slowly reassembling itself. Across North America, the retreat is even more monumental. The Laurentide ice sheet still sprawls over enormous distances, but its margins are in retreat, and those margins define the possibilities of the continent. South of the ice, broad plains and parklands shift as climate softens. To the west, glacial meltwater pours through channels on a scale almost difficult to picture now, reshaping valleys and flooding basins. To the east and north, proglacial lakes collect along the melting front, trapped against ice walls or held by unstable moraines. Some of them are vast enough to resemble inland seas. They shimmer under short summers, cold and heavy with suspended sediment, and behind their shorelines lies a simple danger: they are temporary. Their existence depends on the shape of ice that is itself disappearing. A lake of that kind is not a permanent feature of the world. It is stored instability. Sea levels are rising too, though not with calm regularity. Water once locked in ice sheets returns to the oceans, and coastlines all over the world begin to migrate inland. Land bridges that had connected continents or regions shrink or disappear. Low coastal plains drown. Estuaries widen. Tidal regimes change. For later historians, so much of this early post-glacial world is invisible because it now lies underwater, including campsites, hunting grounds, and migration corridors that people once knew as dry land. What survives in the record suggests that the geography familiar to late Ice Age communities is often larger than the geography inherited by the Holocene. Shores sit farther out. River mouths open into different terrain. Islands are not yet islands. The world is more spacious in some places, but it is also becoming less permanent. The warming of this interval does not create comfort in any modern sense. Even during the Burling Alarud, climate remains cooler than today in many regions, and the atmosphere of the late Pleistocene still dominates the broad frame of life. But relative warmth matters. A few degrees, spread across seasons, can redraw ecological boundaries. Longer growing seasons mean more plant productivity. Reduced snow cover changes grazing access. Thawing ground alters drainage patterns and vegetation communities. Lakes and marshes multiply. Forest edges move. Entire food webs adjust. Large herbivores track these changes because they must. Predators track them too. Human groups, equally dependent on mobility and seasonal knowledge, move through a world whose opportunities are expanding, but whose rules are not yet stable enough to trust. This is the strange gift of post-glacial warming. It creates abundance and uncertainty together. In some landscapes, there is more edible plant life, more fish in thaw-fed waters, more birds in wetlands, more edge habitat where different species overlap. At the same time, familiar routes become unreliable. Meltwater floods can transform valleys in a short span. Softened ground becomes treacherous. Rivers that once froze predictably may now break differently, earlier or with more violence. Permafrost weakens in patches, changing the strength of the land underfoot. Hillsides shed sediment into streams. Lakes expand or vanish as drainage patterns reorganize. The old hard logic of glacial survival is loosening, but what replaces it has not yet settled into anything as dependable as the later Holocene. For human communities, this warming phase offers new territory. People are already highly adaptable, highly observant, and capable of making fine-grained decisions about landscape. They do not wait passively for the world to improve. They expand into openings as soon as openings exist. In Europe, groups follow reindeer, horse, red deer, and other prey into zones once rendered marginal by extreme cold. In Southwest Asia, warming supports richer stands of wild cereals and broader ecological diversity across parts of the Levant and surrounding regions. In the Americas, human populations continue moving through environments that are changing quickly and unevenly, with some regions opening ecologically while others remain sharply constrained by ice, altitude, or aridity. The evidence remains incomplete, especially because many sites are deeply buried, eroded, or drowned by rising seas. But the broad pattern is clear. This is a time of movement, experimentation, and recalibration. Animals respond just as dynamically. Some species thrive as warming expands their preferred habitats. Red deer move into recovering woodlands, Wild cattle and boar gain ground in regions where vegetation grows denser and more varied. Smaller mammals tied to shrubs and forests begin appearing more often in places that had once favoured open, cold-adapted fauna. Yet the warming does not simply erase the old Ice Age community. Reindeer remain important across wide areas. Mammoths still survive in some northern and continental settings. Horses continue using open grasslands where they persist. What emerges is overlap and unstable coexistence of older cold-adapted worlds and newer temperate possibilities. It is a transitional ecology, neither fully glacial nor fully modern, and transitional ecologies often carry hidden strain. One of the lesser-known details of this period is how rapidly plant communities can signal change even before a landscape looks visibly transformed at larger scale. Pollen records show that small adjustments in temperature and moisture can quickly alter the relative abundance of species, especially pioneer trees like birch. A human observer standing in one valley might still feel they inhabit a cold world of open ground and scattered cover, while the microscopic record already shows a measurable shift toward warmer conditions. The Earth begins changing before anyone can name the change, and sometimes before anyone can fully see it. This is why the post-glacial world matters so much to later scientists. It is not just the background to the Younger Dryas. It is the condition that makes the later reversal legible. First, the planet warms enough to begin reorganizing. Only then can the shock of renewed cold stand out so sharply in the record. In Greenland, the ice itself stores this warming in annual layers. Snow falls, compresses, and locks tiny bubbles of ancient atmosphere inside a growing archive. Ratios of oxygen isotopes shift with temperature. Dust concentrations change with atmospheric circulation and dryness. Layer by layer, year by year, a high-latitude memory accumulates. Those ice cores later reveal that the warming into the Bulling Alarud is abrupt, and the contrast matters. The world entering the Younger Dryas is not a world stably cold for thousands of years. It is a world that has already proven capable of fast change. That makes the later reversal more alarming, not less. It means instability is built into the transition. In the North Atlantic, that instability is especially important. Warmth in Europe and Greenland is tied not only to greenhouse gases and solar geometry, but to the circulation of the ocean itself. Heat is transported northward by currents that are sensitive to salinity, temperature, and the formation of deep water. Fresh water from melting ice sheets can interfere with that system. Sea ice responds to temperature and circulation changes. Winds reinforce some patterns and weaken others. The result is a climate engine whose components are connected tightly enough that disruption in one part can ripple outward. During the warmer interval before the Younger Dryas, that engine appears to be functioning in a way that supports significant northern warming. It is not invulnerable. It is merely working for the moment. Farther south, regions respond in their own ways. Rainfall belts shift with changing temperature gradients. Monsoon systems may strengthen or weaken depending on the arrangement of land, sea, and atmospheric circulation. Some areas become wetter as warming reorganizes moisture pathways. Others remain dry or become more seasonally unstable. One reason the post-glacial world is so difficult to summarize is that there is no single version of it. The old ice sheets dominate the north, but their retreat affects the whole planet through sea level, ocean circulation, albedo, and atmospheric dynamics. A warming world is opening, but it opens unevenly. That unevenness is not a side note. It is part of the machinery of the later crisis. For people on the ground, however, these global systems are invisible. What matters is that some places are becoming easier to inhabit. The Near East offers one of the clearest examples. In parts of the Levant, Communities associated with the Natufian culture begin developing more settled patterns than many earlier hunter-gatherers. They gather abundant wild cereals, exploit diverse local resources, build substantial structures in some locations, and show signs of repeated occupation. This is not farming in the full later sense, and scholars still debate the exact degree of mobility in different Natufian communities, but it marks a notable shift in how some people relate to place. The world seems, briefly, to allow longer stays. That brief permission may be one of the most important atmospheric moods of the whole story. After the severity of the glacial maximum, the warming interval invites life to lean outward. It encourages roots, literal and figurative. Trees advance, wetlands spread. Animals enter new ranges. Human groups begin relying more deeply on particular local ecologies, where those ecologies become rich enough to support it. Yet beneath this opening lies volatility. The ice sheets are still there. Meltwater lakes still hold behind weak barriers. Ocean circulation still depends on delicate balances. The Younger Dryas is not an external interruption descending onto a settled world. It is the exposed nerve of a transition already under tension. And that is why the later return of cold feels so devastating in the record. It does not strike a static glacial world that already expects hardship. It strikes a recovering world, one that has begun to reorganize around the possibility of continued warming. Plant communities are shifting northward. Animals are adapting to broader ecological mosaics. Human groups are testing new patterns of movement and settlement in landscapes that appear increasingly generous by late Pleistocene standards. Then the promise falters. The map being drawn by Thor will water, and expanding life is smudged by another abrupt turn. For a short span in geological time, Earth seems to practice a future it will not fully keep. The glaciers retreat, the air softens, and whole regions begin imagining a different climate simply by living inside it. Then, around 12,800 years ago, something tips. The warmer interval that had begun to transform the northern hemisphere does not proceed smoothly into the stable age to come. Instead, the thaw hesitates. The cold comes back, and the fragile new world learns how quickly opening landscapes can close again. At first, the change may not look like the arrival of a new age. It may look like a bad sequence of seasons, a colder spring, a summer that never quite ripens, snow lingering where it should already be gone, a marsh staying locked longer into the year, herds arriving late or not arriving in the same numbers, winds that seem to come from the wrong quarter more often than they used to. For people living through it, there is no single morning when the Younger Dryas begins with ceremonial clarity. Climate rarely works that way on the ground. It gathers in broken signs. But in the archives of the planet, where annual layers and chemical traces accumulate without memory or opinion, the message is sharper. Around 12,800 years ago, the warming trend that had been pulling Earth out of the Ice Age suddenly stumbles. In the North Atlantic world especially, temperatures fall hard, the thaw reverses, the cold arrives fast. The Younger Dryas survives because the Earth keeps records in places human beings rarely think to look. Not in libraries, not in monuments, not in any inscription carved for future eyes, but in ice compressed from ancient snowfall, in dark layers of lake mud, in cave stone that grows one drip at a time, and in sediments spread quietly across the ocean floor. The event leaves no chronicler in the ordinary sense. No one writes that the summers failed, that the cold returned, that forests withdrew and dust rose from bare ground. And yet in a different way, everything writes it. The world records its own disturbance continuously, through chemistry, pollen, shells, charcoal, isotopes, trapped air, and the faint annual patterning of seasons laid down one over another for thousands of years. To understand how scientists reconstruct a climate shock 12,800 years old, it helps to begin with the simplest fact: landscapes remember differently, but they do remember. Greenland is where the memory becomes most dramatic. High on the ice sheet, snow falls year after year and does not fully melt away. Each winter and summer leave subtly different layers. Over time, the weight of later snowfall compresses the older layers into ice, sealing tiny bubbles of ancient atmosphere inside them. Those bubbles are not metaphors. They are real samples of old air, preserved at the time they were trapped. Alongside them, the ice itself carries information in the ratio of certain isotopes, especially oxygen and hydrogen, which shifts according to the temperatures under which the snow originally formed. Drill deep enough into the ice sheet and each meter is a descent through time. Scientists pull up long cylinders of ice, sometimes several kilometers deep, and read them like an archive built by weather. This is one of the reasons the Younger Dryas has become such a central case in paleoclimate science. Greenland ice cores show the transition into the cold phase with astonishing clarity. The isotopic signal changes abruptly. Dust concentrations rise. Other chemical traces shift as atmospheric circulation changes. In some stretches, the annual layers can be counted with enough resolution to reveal that the onset of cooling is not a vague smear over centuries, but something much sharper. Scholars still debate the exact speed and the best way to align different records, and the evidence remains incomplete in the strict sense that all ancient evidence is incomplete. But Greenland offers something rare in deep time history, a sequence so detailed that the cold feels almost visible as it arrives. The trapped gases matter as much as the ice itself. Tiny air bubbles preserve past concentrations of greenhouse gases like methane and carbon dioxide. These do not explain the Younger Dryas on their own, but they help situate it within the broader behavior of the atmosphere. Methane, in particular, often tracks changes in wetlands and tropical hydrology, offering clues about how climate shifts affect distant parts of the planet. Even when the strongest temperature signal comes from Greenland, the atmosphere hints at larger rearrangements in rainfall, ecosystems, and biogeochemical cycles. A climate event is never just temperature. It is circulation, moisture, seasonality, vegetation, dust, fire, and the pace at which entire systems begin talking to one another differently. But ice alone cannot tell the whole story. Greenland is a powerful witness, yet it is one witness in a global case. To understand how the cold affects continents, lakes become essential. At the bottom of a quiet lake, year after year, fine particles settle out of the water clays, silts, pollen, insect remains, algae, bits of charcoal from distant or local fires, fragments of leaves, and the chemical residues of whatever is happening in the watershed around it. If conditions are right, these materials form distinct layers. Some lakes preserve annual laminations known as varves, thin couplets that reflect seasonal deposition. Others build a slower, less regular, but still readable sequence. In both cases, the bottom mud becomes a timeline. Pollen is one of the most elegant tools in that timeline. Plants release vast numbers of pollen grains, and many of them survive burial remarkably well. Under a microscope, different species produce recognizably different shapes. By examining the changing proportions of pollen in successive layers, scientists can reconstruct broad shifts in vegetation over time. If tree pollen declines and pollen from cold-adapted herbs and shrubs increases, the landscape is telling a story of cooling or drying, or both. This is how the Younger Dryas first became legible in many European records. The reappearance or expansion of pollen from Dryas octopetala and other cold-loving plants signaled that warming had reversed. A flower no larger than a hand becomes evidence that a continent changed direction. Pollen, however, is not the same as climate in any simple sense. It reflects vegetation, and vegetation reflects a combination of temperature, moisture, soils, disturbance, competition, and local geography. This is where paleoclimate science becomes as much interpretation as measurement. A rise in birch pollen may suggest warming, but it can also depend on migration rates and local soil development. A decline in woodland taxa may reflect colder conditions, but perhaps also fire, aridity, or human activity in later periods. Scientists do not treat any single proxy as a final answer. They build confidence by comparing many kinds of evidence at once. If pollen shifts, beetle remains suggest colder summers, lake chemistry changes, and glacial activity increases, the picture becomes harder to dismiss. Beetles are a particularly striking example because many species are exquisitely sensitive to temperature. Their remains, preserved in sediments, can indicate the likely range of summer and winter conditions that prevailed when they lived. In parts of Europe, fossil beetle assemblages have helped reconstruct Younger Dryas cooling in surprisingly fine ecological detail. This is one of the quieter wonders of paleontology and paleoecology, that an insect shell buried for over 12,000 years can help estimate the feel of an ancient season. A cold summer can survive in the fragments of a beetle. Charcoal in lake sediments adds another layer. Tiny particles of burned plant matter settle into lakes after wildfires, either from nearby catchments or from farther afield depending on particle size and transport. Peaks in charcoal abundance can indicate changes in fire frequency or intensity, which may reflect shifts in vegetation, aridity, lightning activity, or human ignition in later periods. During times of climatic stress, fire regimes can change dramatically. This does not always yield a neat global pattern, but it helps reveal whether a cooling event is also associated with broader ecological instability. In some Younger Dryas discussions, charcoal becomes especially important because of claims tied to the controversial impact hypothesis. But even outside that debate, fire is part of how disturbed landscapes register change. Ocean sediments preserve another archive, and in many ways an even more expansive one, over thousands of years. The seafloor accumulates the shells of microscopic organisms, mineral particles washed or blown from land, bits of organic matter, and chemical signals locked into sediment grains. Cores taken from the North Atlantic can reveal changes in sea surface temperature, salinity, sea ice extent, and the strength or position of major currents. Tiny foraminifera, single-celled marine organisms with calcium carbonate shells, are especially useful. Different species prefer different water masses. Their abundance and isotopic composition can help reconstruct past ocean conditions in remarkable detail. This matters because the leading explanation for the Younger Dryas involves the ocean directly. If a large pulse of fresh water enters the North Atlantic, it can reduce salinity at the surface. That makes surface waters less likely to sink, and the sinking of cold, salty water is a crucial part of the overturning circulation that helps move heat northward. If the circulation weakens, the North Atlantic region cools. Ocean cores help test this idea by showing whether marine conditions changed in ways consistent with disrupted circulation. In many records, they do. There are signs of cooler surface waters, shifting distributions of microfossils, and other indicators of altered ocean structure, But as always, the details are difficult. Different cores sample different places, and ocean systems are not static pipelines. They shift in space as well as intensity. Interpreting them requires care. Then there are caves, which seem at first like unlikely climate archives. Yet stalagmites and stalactites grow from dripping water that carries dissolved minerals. As the water deposits calcium carbonate, the formations grow layer by layer. Their chemistry reflects the isotopic composition of rainfall, evaporation patterns, vegetation above the cave, and sometimes temperature or moisture balance more broadly. By dating these layers precisely, scientists can reconstruct changes in hydroclimate over long spans, in monsoon regions, Mediterranean settings, and other areas sensitive to rainfall shifts. Cave records can be invaluable. They often show that the Younger Dryas is not only a story of cold, but of altered water. Rains weaken in some places, intensify in others, and the seasonal pulse of moisture changes across entire regions. No archive is perfect. Ice layers thin with depth. Lake sediments can be disturbed by burrowing organisms, slope failures, or changes in basin shape. Ocean cores may compress time unevenly or contain gaps. Cave records can be difficult to interpret when multiple climatic influences overlap. Radiocarbon dating, one of the most important chronological tools for this period, must also be calibrated carefully because the amount of radioactive carbon in the atmosphere has varied over time. Dates do not emerge from ancient material as ready-made truths. They are built through statistical models, calibration curves, comparison with other records, and often a great deal of argument. Scholars still debate the precise alignment of certain Younger Dryas signals between different regions. And these debates matter because causation depends on sequence. If one place changes slightly before another, the mechanisms might be different than if all changes are truly simultaneous. This is why paleoclimate work can feel both exact and uncertain at the same time. A single core may show a beautiful, sharp transition, but when that core is compared with others from far away, different sedimentation rates, dating methods, seasonal biases, and local ecological responses complicate the picture. The evidence is powerful precisely because it comes from many sources, yet no two sources speak in quite the same language. Scientists spend years aligning them, testing them, questioning whether one proxy reflects annual temperature while another reflects summer moisture, whether one archive is recording a regional shift and another a global one. The Younger Dryas remains such a compelling mystery partly because the records are rich enough to demand explanation, but diverse enough to resist easy closure. Sometimes the strangest clues are the smallest. A shift in the wax chemistry of ancient plant leaves buried in sediments can hint at changing rainfall sources. The size distribution of dust grains can suggest stronger winds or closer sediment sources. Diatoms, microscopic algae with silica shells, respond to salinity, nutrient balance, and lake stratification. Ancient DNA preserved in sediments can reveal the presence of plants or animals even when no visible remains survive. As methods improve, the record becomes more crowded with testimony. The world keeps producing new witnesses long after the event itself. And yet, for all this technical sophistication, the essential picture is still rooted in something almost simple. The Younger Dryas is visible because many different parts of the Earth system register the same interruption. Ice grows colder in its isotopic signature. Dust rises. Pollen shifts toward cold-adapted vegetation. Ocean conditions reorganize. Lake ecosystems change. Rainfall patterns move. Fires, in some places, leave altered traces. Glaciers in some mountain regions pause or advance. Together, these signals say the same thing in different ways. The warming world faltered and the climate turned hard again. What scientists inherit, then, is not a single perfect narrative, but a chorus of partial ones. Each archive preserves one angle of the event. Greenland tells of abrupt northern cooling. European lake sediments reveal ecological retreat. North Atlantic cores speak of disrupted marine conditions. Caves record altered rainfall. Together they reconstruct an ancient shock without ever allowing anyone the luxury of total certainty. That tension is not a flaw. It is the reality of reading a vanished world through the materials it left behind. And once the evidence is assembled, one explanation begins to stand above the others, not because it solves every detail, but because it matches so much of the pattern. Somewhere amid the melting ice sheets, the great proglacial lakes, and the delicate circulation of the North Atlantic, fresh water appears to hold the key. The question is not only whether water mattered, but how a flood of it could push an entire climate system into reverse. The leading explanation begins not in the sky, but in water. Not ordinary water moving through ordinary rivers, but glacial meltwater on a continental scale, fresh, cold, and destabilizing. By the time the Younger Dryas begins, the great ice sheets of the northern hemisphere are already in retreat, and retreat on that scale does not produce neat drainage. It produces chaos held together temporarily by ice, sediment, gravity, and chance. Along the margins of the Laurentide ice sheet in North America, meltwater gathers in enormous proglacial lakes. Some of these water bodies are so vast that calling them lakes feels strangely inadequate. They are inland seas bordered by ice walls and unstable terrain, storing volumes of fresh water capable of altering coastlines, rivers, and perhaps, under the right conditions, the climate of the entire North Atlantic world. This is the logic behind the meltwater trigger, the Atlantic meridional overturning circulation, the broad system of currents that helps carry warm surface water northward and return colder deep water southward, depends in part on the sinking of cold, salty water at high latitudes. Salinity matters because salt makes seawater denser. In the North Atlantic, where surface waters cool, become heavy, and sink. That density structure helps power a global-scale circulation pattern. If enough fresh water is added to the surface ocean, salinity drops. If salinity drops enough, surface waters become less likely to sink. If sinking weakens, the circulation can slow, and if the circulation slows, less heat is transported north. The North Atlantic region cools. Sea ice may expand, and a whole suite of atmospheric feedbacks can begin reinforcing the change. In principle, it is a beautifully coherent mechanism. It explains why the Younger Dryas is so strongly expressed around Greenland and the North Atlantic. It fits with marine evidence suggesting altered ocean circulation. It matches the broader understanding that deglaciating worlds are vulnerable to freshwater pulses. It also has a certain grim elegance. A warming climate melts ice. Melting ice releases fresh water. Fresh water disrupts the system, helping maintain regional warmth. Regional warmth collapses. The thaw sabotages itself. Earth, at the edge of deglaciation, seems to generate its own relapse. But as with all explanations that rise to prominence, the moment one becomes persuasive in broad outline, its details begin causing trouble. Which body of fresh water is responsible? How exactly does that water reach the ocean? In what quantity, over what time scale, does the circulation weaken suddenly because of a single catastrophic drainage event, or because of repeated pulses and cumulative stress? And why do some geological traces suggest routes and timings that do not align neatly With the onset of the Younger Dryas, scholars still debate these questions intensely, not because the freshwater idea is weak, but because it is strong enough to deserve serious testing. One of the central figures in this story is glacial Lake Agassiz, or more accurately, the shifting complex of proglacial lakes that occupied parts of central North America during deglaciation. At different times, these lakes cover enormous areas across what is now Canada and the northern United States. Their shorelines move as the ice retreats and drainage pathways open or close. The amount of water involved is difficult to overstate. In a modern imagination trained by familiar maps, it helps to picture a fluid geography where entire inland regions can become temporary basins of cold, fresh water, held in place by barriers that are neither ancient bedrock nor permanent coast, but retreating ice and fragile sedimentary dams. These lakes are not stable features of the world, they are stored release. For decades, one influential version of the Younger Dryas trigger holds that a major outburst from Lake Agassiz or related proglacial waters drains eastward into the North Atlantic, freshening critical regions where deep water normally forms. The flood need not be visible everywhere in one neat geological scar to have climatic consequences. What matters is that sufficient freshwater arrives in the wrong place within the ocean system. Once there, it suppresses overturning, cools the North Atlantic, and helps initiate the cold phase. In climate modelling and conceptual terms, the mechanism makes sense. It is consistent with the broader behaviour of the ocean atmosphere system, and it draws support from the fact that modern observations and models also treat overturning circulation as sensitive to freshwater forcing. Yet the geological record is stubborn. Some proposed drainage routes appear less certain under closer examination. Some dates once thought to align perfectly with the onset of the Younger Dryas have been revised. In some cases, landforms attributed to a catastrophic eastward flood are reinterpreted or considered difficult to tie securely to the right moment. Alternative routes have been proposed, including northward drainage into the Arctic and then into the North Atlantic system by more complex paths. That possibility changes the geometry of the problem. A flood entering the Arctic Ocean, or distributed through multiple outlets, may still influence circulation, but not in the simple way earlier models imagined. The evidence remains incomplete, and no single hydrological scenario has gained universal acceptance. This is one of the quieter lessons of paleoclimate science. A mechanism can be broadly right, while its historical particulars remain uncertain. Freshwater forcing may still be the correct family of explanation, even if the exact source lake, drainage route, or flood timing is not yet fully resolved. Scholars sometimes disagree not about whether freshwater matters, but about which freshwater, how much of it, and whether the critical disturbance is a short catastrophic pulse or a more prolonged reorganization of meltwater routing over time. The ocean does not care whether human categories feel tidy. It responds to boundary conditions, thresholds, and feedbacks. There is also the question of how much fresh water is enough. Some climate models suggest that a sufficiently large pulse can produce substantial weakening of the overturning circulation and cooling over the North Atlantic region. Others indicate that the response depends on the background climate state, the exact location of input, sea ice conditions, and the interaction with winds and atmospheric feedbacks. A deglaciating world is not the same as the modern world. Ice sheets are larger, sea level is different, coastlines are different, and the ocean circulation itself may already be in a more delicate configuration. That means the same volume of fresh water might have different consequences in different climatic contexts. This is important because it may help explain why the Younger Dryas occurs when it does, rather than earlier or later in deglaciation when meltwater is also abundant. One lesser-known complication is that not all freshwater signals are equally visible in the geological record. Ocean sediments do preserve evidence of surface freshening and circulation changes, but these signals can be patchy, redistributed, or obscured by later processes. Fresh water entering the ocean can spread unevenly, mix seasonally, and interact with sea ice in ways that make a clean fingerprint difficult to isolate. It is entirely possible for the climate system to react strongly to a disturbance that later leaves a more ambiguous physical trace than one might wish. Scientists are therefore often forced to reason from convergence climate models, marine cores, terrestrial records, and glacial reconstructions, all pointing toward the same broad story, even if none provides a complete diagram of the event. Sea ice may be the missing accomplice that turns a freshwater disturbance into a durable cold state. Once surface freshening and cooling begin reducing overturning, sea ice can expand across parts of the North Atlantic. Expanded sea ice reflects more sunlight, suppresses heat exchange between ocean and atmosphere, and can shift atmospheric circulation patterns. Cold conditions then become easier to sustain. In that sense, the freshwater flood is not necessarily the whole cause, but the shove that tips a balanced system into a new mode. Afterward, feedbacks do much of the work. This is another reason the Younger Dryas matters so much today. It shows how quickly a system can reorganize when several linked components begin amplifying one another. The event's very abruptness in Greenland has pushed researchers to ask whether ocean circulation can really respond that fast. Increasingly, the answer seems to be yes, at least regionally and under the right conditions. Climate does not always shift in proportion to forcing the way ordinary intuition expects. It can remain stable while pressure builds, then change rapidly once a threshold is crossed. The meltwater trigger is compelling because it fits that threshold behavior. So long as deep water formation continues, northern warmth can persist. But once salinity and sea ice cross a critical point, the system may reorganize surprisingly quickly. The warming world does not have to fade gradually into cold. It can tip. There are other freshwater candidates as well. Some reconstructions point toward changing drainage from Fennoscandian ice sheets in northern Europe. Others emphasize a broader cumulative restructuring of meltwater pathways from multiple sources rather than a single giant flood. Still others suggest that the North Atlantic circulation may already have been unstable, requiring only a moderate perturbation to shift. No single explanation fully accounts for the exact geography of every freshwater input, and the further back scientists reach into deglaciation, the more the land itself refuses modern assumptions. Shorelines are displaced, channels are buried. Isostatic rebound has lifted some regions and lowered others. The map is not fixed, which makes tracing ancient water far harder than drawing lines across a present-day atlas. Even so, the freshwater hypothesis remains the dominant explanation, because it aligns with too many elements of the event to dismiss. It explains why the strongest cooling centers on the North Atlantic. It matches evidence for circulation changes in the ocean. It fits the deglacial setting, where immense freshwater reservoirs are unquestionably present. It also helps account for the duration of the Younger Dryas, especially if feedbacks involving sea ice and atmosphere can help maintain the cold state once initiated. The main resistance to the theory is not that it lacks plausibility, but that the ancient world rarely preserves mechanisms in the clean forms modern minds prefer. For the people and animals living through the transition, none of this hidden oceanic drama is visible. There's no sign on the horizon that says overturning circulation has weakened. There is only the practical result. The winds seem harsher, the seasons tighten. Cold lingers in regions that had been warming. Moisture patterns shift. the ecological opportunities created by retreating ice begin to contract again. Somewhere far to the northwest or north, meltwater may be pouring through new channels, spreading across seas, and altering density structures in waters no human group of the time can fully comprehend. But they do not need to comprehend the mechanism to live inside the consequence. And yet the freshwater story, for all its strength, is still not enough to satisfy everyone. The sheer abruptness of the onset, the coincidence with broader environmental disturbance in some records, and the enduring human appetite for singular catastrophe ensure that another theory enters the debate and refuses to leave. According to that idea, the trigger does not come from glacial water at all, but from space. Not a flood from a melting continent, but a blow from above. It is a theory with drama built into its bones, and that is one reason it travels so far. The idea is almost irresistible. A comet, or fragments of one, enters Earth's atmosphere near the beginning of the Younger Dryas. Perhaps it explodes in the air. Perhaps some fragments strike the surface. Fires spread across continents. Dust and soot rise into the sky. Ecosystems already under stress are pushed into collapse. The climate system is jolted hard enough to tip back toward cold. For many people encountering the Younger Dryas for the first time, this explanation feels instinctively satisfying. It offers a single dramatic cause for a dramatic event. It has flame, impact, sky, shock, and the familiar appeal of cosmic violence. It turns a difficult paleoclimate problem into something closer to a prehistoric disaster film. That, in itself, is one reason for caution. The Younger Dryas impact hypothesis first gains broad attention in the early 21st century, when researchers proposed that an extraterrestrial event around 12,800 years ago helps trigger the climatic reversal, and perhaps contributes to broader ecological and cultural disruptions, including the decline of North American megafauna and the end of the Clovis archaeological tradition. The claim is bold because it attempts to tie together several major transitions at once. A single catastrophe, arriving from space, would explain sudden cooling, widespread burning, extinctions, and cultural change in one sweeping gesture. It is a powerful narrative. But powerful narratives are not the same thing as strong evidence. Supporters of the hypothesis point to several kinds of material they argue are markers of impact or atmospheric explosion. These include microspherules formed under extreme heat, nanodiamonds, elevated concentrations of certain elements such as platinum, melt glass, magnetic grains, and soot or charcoal layers that they interpret as signs of unusual burning. At some sites, proponents identify what they call a Younger Dryas boundary layer, a sedimentary horizon that appears to coincide with the onset of the event. If such a layer truly recorded an impact-related episode across multiple regions, it would be remarkable. It would suggest that the beginning of the Younger Dryas is not merely a climatic threshold crossed within the Earth system, but a planetary disturbance imposed from outside. There is a reason this argument captures public imagination so strongly. Humans are drawn to discrete moments, to singular causes, to stories in which one terrible event reshapes everything after it. Geological and archaeological records, by contrast, are usually untidy. They preserve staggered changes, incomplete sequences, regional variation, and long durations. The impact hypothesis cuts through that untidiness with an almost mythic simplicity. Something falls. The world changes. It is easy to see why such a theory spreads beyond technical journals into documentaries, articles, and popular retellings. It offers the pleasure of narrative compression, but the scientific response has been cautious to sharply critical. and over time most specialists in paleoclimate, quaternary science, archaeology, and impact geology remain unconvinced that a comet or impact event explains the Younger Dryas onset. The reasons are several, and they matter. Many of the proposed markers have proved difficult to reproduce consistently across different laboratories and sites. Some materials identified as impact-related may also form through terrestrial processes such as wildfire, volcanic activity, normal sedimentary reworking, or industrial contamination in modern handling if procedures are not careful enough. Some supposed boundary layers appear less synchronous than first claimed. Others are real layers, but their interpretation remains disputed. In science, a pattern that cannot be replicated reliably does not become stronger through repetition in popular media. It becomes weaker. One of the central problems is scale. A true impact or airburst large enough to trigger a millennium-long climate reversal should, in principle, leave robust and unmistakable evidence. Known large impacts tend to leave craters, widely distributed ejecta, or geochemical signatures that can be traced with confidence. Supporters of the Younger Dryas hypothesis sometimes argue for fragmented airbursts or impacts on ice, which might reduce crater formation and make the event harder to detect. That is not impossible in principle. Earth has experienced atmospheric explosions, and icy surfaces complicate the record. But as the hypothesis becomes more flexible in order to explain the absence of expected evidence, critics argue that it also becomes harder to test cleanly. A theory that can accommodate almost any lack of confirmation begins to lose explanatory discipline. Platinum anomalies have often been presented as one of the stronger pieces of supporting evidence, since elevated platinum in some sediment layers near the Younger Dryas boundary might indicate extraterrestrial material. Yet even here the picture is complicated. Some sites do show intriguing enrichments, but not all, and the meaning of those enrichments is debated. A platinum spike by itself does not automatically prove a catastrophic impact responsible for the entire Younger Dryas. It might signal a more limited event, local processes, or contamination pathways still being sorted out. Science is full of suggestive clues that do not mature into decisive conclusions. The evidence remains incomplete, and that phrase matters especially here. Wildfire evidence is similarly contentious. Some proponents describe continent-scale burning at the onset of the Younger Dryas, an ecological shock large enough to darken skies and devastate landscapes. Yet fire is a common feature of many ecosystems, and charcoal layers can be produced by ordinary though still intense burning linked to drought, changing vegetation, lightning, or local circumstances. Regional spikes in charcoal do not necessarily add up to a single extraordinary inferno. In some places there is no clear evidence for the scale of fire the impact model would seem to require. In others, burning may well have increased, but for reasons that do not demand a cosmic trigger. When a climate system is already destabilizing, landscapes can burn more readily without help from the heavens. The effort to link the hypothesis to megafaunal extinction also runs into trouble. Large Ice Age animals such as mammoths, mastodons, giant ground sloths, and others do disappear around the terminal Pleistocene, but not all at once, not everywhere simultaneously, and not in a pattern that fits neatly with a single impact event. Some populations decline before the Younger Dryas. Some survive well into it or beyond in refugial contexts. Human hunting pressure, habitat fragmentation, changing vegetation, climatic stress, and complex ecological interactions all likely contribute. Scholars still debate the weighting of these factors, but most reject any simple one-cause account. The extinction story is already complicated before the impact hypothesis arrives, and it remains complicated afterward. The same is true of Clovis archaeology in North America. The end of the classic Clovis horizon roughly overlaps the Younger Dryas boundary, but cultural transitions do not automatically imply catastrophe from space. Technologies change, populations move, regional traditions diversify. Preservation bias shapes what survives in the record. To many archaeologists, the attempt to fuse climatic reversal, extinction, and cultural change into a single instant event seems less like explanation and more like narrative overreach. Deep history rarely grants that kind of neat alignment. Still, the hypothesis does not disappear. Partly this is because some evidence remains intriguing enough to keep the conversation alive. Partly it is because a small number of studies continue reporting boundary markers that supporters interpret as extraordinary. And partly it is because the idea answers an emotional need in the modern imagination. A sudden freeze feels like it ought to have a sudden cause. Ocean circulation, by contrast, feels too abstract, too hidden, too technical. Water density and sea ice feedbacks do not satisfy the same instinct for spectacle. Yet nature does not organize itself around what humans find dramatically convincing. A quiet change in salinity can alter a climate just as surely as a flaming object in the sky, and perhaps more plausibly in this case. There is also a deeper issue beneath the debate. The impact hypothesis tends to frame the Younger Dryas as a singular, external shock descending on an otherwise understandable transition. The freshwater and circulation model frames it as an expression of instability already present within a deglaciating Earth system. Those are very different philosophies of causation. One points outward, the other points inward. One emphasizes catastrophe, the other emphasizes thresholds. The second is less cinematic, but it may also be more unsettling, because it suggests that the planet does not need an asteroid to produce abrupt and dangerous change. It can do that on its own. That said, it would be too simple to treat the impact hypothesis as pure fantasy. It is better understood as a controversial attempt to explain real features of the record that are themselves worth examining. Some sediment layers near the Younger Dryas boundary do contain unusual materials. Some environmental disruptions do cluster around the onset. Some questions about abruptness remain difficult. Fringe theories often fail because they are entirely disconnected from evidence. This one persists because it engages with genuine anomalies, even if most researchers believe it misreads or overstates them. The distinction matters. Unsupported does not mean invented from nothing. It means not sufficiently demonstrated. In the end, mainstream opinion remains where it has increasingly settled. The impact hypothesis has not met the evidentiary standard required to explain the Younger Dryas as a whole. There is no widely accepted crater of the right age and context, no globally consistent impact layer beyond serious dispute, and no consensus that the supposed markers require extraterrestrial origin. The theory remains in the literature and in public discussion, but at the margins of the scientific explanation rather than its centre. The stronger case still lies with freshwater forcing, ocean circulation change, and feedbacks involving sea ice and atmosphere. Yet the debate has not been useless. On the contrary, it has forced closer examination of sediment layers, improved methods for identifying extreme temperature particles, sharpened chronological comparisons, and drawn attention to how difficult it is to separate abrupt environmental changes from one another in the terminal Pleistocene. Even disputed hypotheses can advance knowledge by compelling better questions. In that sense, the comet has performed a kind of service even if it never truly arrived. And the Younger Dryas does not need a cosmic impact to be extraordinary. Once the climate system begins to shift, the consequences spread through wind, water, vegetation, and fire in ways dramatic enough on their own. Dust increases, rainfall belts move, sea ice grows, landscapes become more brittle and less predictable. The disturbed planet begins sending signals far beyond the immediate zone of cooling, leaving evidence not of one simple freeze, but of a wider environmental reorganization. Once the Younger Dryas begins, the planet does not merely become colder in a narrow and isolated sense. It becomes unsettled. Cold is the headline. But disturbance is the full story. The most revealing signals are not always those of temperature alone, but of systems falling out of their earlier balance. Winds change their behavior. Dust moves differently across continents. Rainfall belts shift. Sea ice expands. Fire regimes alter in some regions. Lakes rise in one landscape and shrink in another. Vegetation responds unevenly, sometimes retreating, sometimes reorganizing, sometimes surviving in stressed fragments. What emerges from the record is not a single frozen tableau, but a disturbed planet expressing its stress through many channels at once. Dust is one of the clearest of these channels. In Greenland ice cores, dust concentrations rise sharply during the Younger Dryas, echoing patterns seen in colder and drier intervals of the last glacial period. Dust matters because it is both a signal and a force. It indicates that somewhere, often far away, landscapes are dry enough, bare enough, and windy enough to surrender fine sediment to the atmosphere. It also affects climate directly by interacting with sunlight, cloud formation, and snow albedo when deposited on ice or land surfaces. An increase in dust suggests stronger winds, expanded aridity, exposed sediment, or all three together. It evokes not just cold, but abrasion, a world less buffered by vegetation, less settled, more vulnerable to the atmosphere scraping across it. In Eurasia, this matters enormously, as warming had previously encouraged shrubs, wetland development, and the first hesitant advance of woodland into some regions. The Younger Dryas checks or reverses part of that trend. Open ground expands again in places. Cold-adapted plants persist or return. Where vegetation cover becomes thinner or more seasonally stressed, soils and silts become easier to mobilize. Loess deposition, the slow settling of wind-blown dust, becomes more active in some regions under cold, dry conditions. Loess is easy to overlook because it arrives grain by grain, but over time it can blanket landscapes in thick yellow-brown mantles. Entire chapters of climatic instability survive in those quiet accumulations of airborne earth. The movement of dust also hints at altered atmospheric circulation. Winds do not strengthen or shift arbitrarily. They respond to gradients in temperature, pressure, sea ice, land cover, and the position of major storm tracks. If the North Atlantic cools and sea ice spreads, the whole structure of the overlying atmosphere can reorganize. The jet stream may shift. Winter storm paths may change. Some regions may become stormier, others drier, others more seasonally erratic. The Younger Dryas, then, is not simply a frozen interruption imposed on otherwise ordinary weather. It is a remapping of circulation, one that changes where moisture travels, where snow accumulates, and where dryness takes hold. This helps explain why rainfall records from the period are so important. In caves, lake sediments, and other hydrological archives. The Younger Dryas often appears as a change in water rather than a dramatic plunge in measured temperature. In parts of Southwest Asia and the Eastern Mediterranean, many reconstructions suggest cooler and drier conditions. Though the local picture varies, what matters is that moisture stress may have intensified precisely in places where late Pleistocene people were beginning to rely more heavily on stable local resources. A few degrees less warmth is one problem. Less predictable rain is another, and in many ways more dangerous. Temperature can make a season harsher. Water decides whether landscapes remain productive at all. Farther afield, monsoon systems seem to shift as the climate reorganizes. The exact timing and magnitude of these changes remain debated, and different proxies do not always line up neatly. But what survives in the record suggests the Younger Dryas affects tropical and subtropical rainfall belts as well as northern cold. This is one of the reasons the event cannot be reduced to a regional curiosity of Greenland and Europe. A weakened Atlantic overturning circulation changes heat distribution across hemispheres. That, in turn, influences atmospheric circulation patterns far from the original zone of oceanic disturbance. Some regions experience drying, others may see altered seasonality or shifted precipitation timing. The disturbed planet sends its signals outward through water. Sea ice is another part of the story, and perhaps one of the most powerful amplifiers. Once cooling begins in the North Atlantic, sea ice can expand southward and persist longer through the year. This matters because sea ice is both barrier and mirror. It blocks heat exchange between ocean and atmosphere, helping keep the air above colder. It reflects incoming sunlight, reducing the amount of solar energy absorbed by the ocean. It can also alter the formation of deep water and influence where storms develop or intensify. In a system already tipped by fresh water and weakened overturning, sea ice helps lock the new state into place. What might otherwise have been a temporary cooling pulse becomes a more durable climatic regime. This interaction between sea ice and ocean circulation creates one of the most revealing patterns of the Younger Dryas. The cold is strongest in and around the North Atlantic, where these feedbacks are most active. But the consequences ripple far beyond that core. In marine sediments, shifts in plankton communities and isotopic signatures reveal cooler surface waters and changing ocean structure. On land, vegetation belts falter. In ice cores, dust rises. In caves, rainfall chemistry changes. Each record is local, but together they describe a connected system. Climate does not move in tidy lines from cause to consequence. It spreads through feedback loops, and feedback loops often produce the kind of wide, uneven disturbance the Younger Dryas displays. Fire adds another layer of complexity. In some regions, charcoal records suggest changes in burning during or near the onset of the Younger Dryas. These signals are not uniform enough to support any simple claim of worldwide fire catastrophe, but they do point toward ecological instability. Fire regimes depend on a strange combination of ingredients: enough plant growth to produce fuel, enough dryness or seasonality to make that fuel burn, ignition sources, and weather conditions that allow fire to spread. A climate shift can alter any part of that balance. In some places, colder conditions might reduce fuel loads or shorten fire seasons. In others, drying and vegetation transition might create more burnable landscapes. The Younger Dryas does not produce one planetary fire story. It produces many local ones, and that variety itself is revealing. One lesser-known detail is how strongly lake systems can respond to this kind of disturbance. Lakes are sensitive not only to rainfall, but to snowmelt timing, evaporation, vegetation cover, erosion, and the chemistry of incoming water. During the Younger Dryas, some lakes show falling levels, others signs of changing stratification, still others shifts in salinity or biological productivity. Diatoms change, organic matter fluctuates. Sediment input rises where vegetation weakens and slopes become less stable. A lake can record a colder world not because ice forms on its surface for longer, though that may happen, but because the whole watershed feeding it begins behaving differently. This is how climate becomes visible as landscape process. There is also the question of seasonality. Not all cold is the same. A region might experience much harsher winters without an equally dramatic drop in summer warmth. Another might lose just enough summer heat to impair plant productivity, even if winters do not become catastrophic. A change in the timing of snowmelt can affect grazing, migration, spawning, and human foraging without any single annual temperature average looking apocalyptic on paper. This is part of why the Younger Dryas is so difficult to compress into simple numbers. It is experienced through seasons, and seasons can change in ways averages conceal. For people and animals, the difference between survival and failure often lies in whether spring arrives when expected, whether summer is long enough, whether rivers open in time, whether food peaks overlap or miss each other. As the atmosphere and hydrology reorganize, so does the emotional geography of the world, though no direct record can capture it. Landscapes that had begun to feel newly available become conditional again. Wetlands that offered birds, reeds, and fish may shrink or freeze longer. Valleys that seem to promise more reliable plant growth become vulnerable to cold snaps or reduced rainfall. Dust in the air, harsher winds, more persistent snow cover, and shifting storm tracks all change the cost of movement. The Younger Dryas is not simply colder space, it is harder space. This broader reorganization also helps explain why no single line of evidence can stand alone. A climate reversal might be visible in pollen without obvious fire change. A hydrological shift might appear in caves where vegetation remains ambiguous. Dust may rise strongly in Greenland even while regional expressions elsewhere remain mixed. The event is large, but the Earth system is not obligated to express large events uniformly. What matters is the convergence. Cold, dryness, altered winds, expanding sea ice, and ecological instability appear together often enough, in enough different forms, to reveal a world under stress. Perhaps the most unsettling part is that none of this requires total collapse to be consequential. The disturbed planet does not need to become uninhabitable everywhere to transform life. It only needs to become less predictable, less generous, and more sharply seasonal in the wrong places. Species already near ecological limits feel that pressure quickly. Human groups relying on local abundance feel it too. The Younger Dryas reminds us that climate stress is often cumulative rather than theatrical. A slightly shorter growing season, a weaker rainfall pattern, a harsher winter sequence, a migration route that no longer yields the same prey, a dustier atmosphere, more sea ice, less reliable water. None of these changes needs to be universal to matter profoundly. And this is where the story begins pressing hardest on the great animals of the late Ice Age: mammoths, giant deer, woolly rhinoceroses in earlier and more eastern contexts, steppe bison, and other large-bodied creatures are not abstract symbols of a lost world. They are living populations with specific habitat needs, migration routes, reproductive limits, and food requirements. Many have already survived enormous climatic shifts before. But survival in one unstable world does not guarantee survival in the next. As the Younger Dryas spreads its cold, dryness, and ecological fragmentation across northern landscapes, the animals that once seemed built for harshness find themselves entering a new kind of pressure. The great animals of the late Ice Age are often imagined as creatures of boundless strength, moving through a world made for them. Mammoths crossing open steppe beneath cold skies, giant deer carrying extravagant antlers through sparse woodland margins, bison and horses spreading across broad grasslands that seem to have no end. There is truth in that image, but only part of the truth. Large animals are never merely symbols of toughness. Their size is also a vulnerability. They need enormous amounts of food, they require space, they depend on seasonal rhythms that must remain predictable enough for breeding, migration, and recovery. They can survive cold astonishingly well if the cold belongs to a stable world. What wears them down is not always severity alone, but instability. And the Younger Dryas is a period of instability sharpened into pressure. By the time this cold reversal begins, many of the great Pleistocene mammals are already living in landscapes that have been changing for thousands of years. The old mammoth steppe, that vast dry and productive belt of grasses, herbs, and sedges stretching across much of northern Eurasia and parts of North America in varying forms, is not simply disappearing overnight, but it is fragmenting. Warming during the earlier deglacial interval has already encouraged the spread of shrubs, wetlands, and trees in some areas. That may sound like ecological richness, and in one sense it is. But what benefits one species can constrain another? Mammoths are not generic cold animals. They are specialists in a particular sort of open, often dry, highly seasonal environment. As the mosaic shifts and then shifts again under Younger Dryas conditions, they face not a return to some ideal former state, but a more broken one. This is a crucial distinction. It is tempting to think that if the Younger Dryas brings back colder conditions, then cold-adapted megafauna should benefit automatically. In practice, the picture is far more complicated. The returning cold does not restore the exact ecological structure of the earlier glacial world. Atmospheric circulation is different. Ice sheets are in retreat. Sea levels are higher. Hydrology has changed. Plant communities have already been disturbed by warming and are now being disturbed again by renewed cold. Some regions become drier, dustier, or more seasonal. Others develop patchier combinations of open ground, shrub tundra, wetland, and early woodland. The result is not a stable pasture for megafauna, but a landscape of interrupted opportunity. For large herbivores, the quality and accessibility of forage matter as much as raw temperature. A mammoth can tolerate severe cold if it can reach enough grasses, sedges, and herbs beneath snow cover. A giant deer can survive impressive winters if its habitat still offers the right mix of browsing and open movement. Reindeer can handle cold brilliantly, but their migrations depend on timing, insect pressure, snow conditions, and vegetation patterns that must remain usable across long distances. Even small changes in snow crusting, spring melt timing, or the spatial distribution of food can carry major consequences over successive years. The Younger Dryas intensifies exactly those kinds of changes. Snow is especially important, and it is one of the least appreciated forces in the story. Deep or badly crusted snow can make forage inaccessible, even when plants remain present below. Freeze-thaw cycles can create hard surfaces that injure animals or prevent them from pouring through to food. Longer snow persistence delays plant emergence in spring, reducing the quality of forage available during critical reproductive periods. Animals living close to the margin of sufficient energy do not need dramatic catastrophe to begin declining. They only need a sequence of difficult seasons with too little room for recovery. The evidence remains incomplete for reconstructing these conditions at every local scale. But what survives in the record suggests that Younger Dryas climates often become more stressful in exactly these practical, seasonal ways. Mammoths occupy a special place in modern imagination, perhaps because they are large enough to feel almost mythical while still being unmistakably real. Yet their final history is messy, regional, and prolonged. They do not all vanish at once when the Younger Dryas begins. In some areas they have already declined. In others, they survive through part or much of the interval. Small isolated populations continue in rare refuges long afterward, most famously on Wrangel Island, though by then they are remnants living far beyond the main terminal Pleistocene collapse. This staggered disappearance is important. It shows that the Younger Dryas is not a single executioner. Rather, it is one phase in a longer squeeze involving habitat fragmentation, climatic instability, and in many places growing human pressure. No single explanation fully accounts for mammoth extinction everywhere. The same complexity surrounds other megafauna, giant deer in Eurasia, with their vast antlers and preference for relatively open but productive landscapes, are vulnerable to the spread of dense forest on one side and the return of harsher, less predictable conditions on the other. In North America, mastodons, mammoths, giant ground sloths, horses, camels, and large carnivores disappear in patterns that vary by species and region. Some likely suffer from changes in vegetation and water availability. Others may be especially vulnerable to hunting pressure because large-bodied animals reproduce slowly and cannot absorb sustained losses easily. Ecological communities under climate stress become less resilient, and less resilient communities are easier for even moderate human predation to destabilize. This is why debates over extinction remain so heated. For decades, arguments tend to swing between climate and humans, as though one must be acquitted for the other to be guilty. In reality, terminal Pleistocene extinctions often look like the outcome of interacting pressures. Climate reorganizes habitats and migration routes. Food webs become patchier. Reproduction suffers. Populations fragment into smaller, more isolated groups. Human hunters, whether newly arrived or increasingly widespread, do not need to kill every animal everywhere to matter. They may only need to remove enough individuals from already stressed populations to prevent recovery. The Younger Dryas matters in this framework because it intensifies vulnerability. It narrows the margin for error. One lesser-known clue to that vulnerability comes from ancient DNA and radiocarbon work showing how fragmented some late populations become before final disappearance. A species may still be present across a broad map in the imagination, yet genetically it can already be breaking into isolated pockets with little resilience. That kind of fragmentation is dangerous even in relatively stable environments. Under climatic stress, it becomes worse. A harsh sequence of years can erase a local herd. A migration corridor lost to changing vegetation or wetland expansion can sever contact between populations. Once fragmentation passes a certain threshold, extinction becomes not dramatic but quiet. Whole regions simply stop yielding bones from later dates. Predators suffer too, though often in ways less visible than the disappearance of giant herbivores. Large carnivores depend on prey abundance, territory, and stable hunting grounds. If herbivore distributions become patchy or populations thin, predators are affected in turn. Some may switch prey, some may shrink in range, some may disappear from whole landscapes even if they survive elsewhere. The end of the Pleistocene is full of these cascading effects, and the Younger Dryas acts as an accelerant within systems already under tension. It is not always the first blow, but often the one that lands when resilience is already compromised. There is also a cruel irony in the Younger Dryas for cold-adapted species. A return to colder conditions might briefly preserve some habitats that warming had begun to erase. But because the event takes place in a world already moving overall toward deglaciation, that preservation is temporary and unstable. The cold buys time without restoring security. Mammoths and other Ice Age survivors are not being returned to their old continent-spanning kingdom. They are being offered scattered reprieves inside a collapsing ecological order. When the Younger Dryas eventually ends, warming resumes and the remaining fragments face renewed pressure from expanding forests, wetlands, changing soils, and increasingly human-shaped landscapes. The pause is real, but it is not salvation. Human beings are part of this story whether one wants them to be central or not. Across Eurasia and the Americas, people are hunters, scavengers, travelers, and competitors moving through many of the same spaces as megafauna. They understand animal behavior closely enough to exploit crossings, seasonal concentrations, or vulnerability during certain times of year. Even small human populations can matter if they are efficient, mobile, and persistent over long periods. At the same time, it would be too simple to imagine humans as a single overwhelming force sweeping all great animals away. The timing and geography are too uneven for that. What the record suggests instead is a more unsettling partnership of causes, climate pressure making large animals less resilient, and humans adding selective mortality in systems already losing their balance. For the animals themselves, none of this appears as theory. It appears as narrower pathways across the land. It appears as forage hidden under hard snow, wetlands in places once traversed easily, spring growth delayed, waterholes altered, calves born into lean years, predators or hunters encountered on routes that used to be safe. Large herbivores live by memory in the practical sense, by returning to places and timings that have worked before. Climate instability punishes that dependence. A known landscape becomes unreliable. Survival strategies built over generations begin to fail. This helps explain why extinctions often feel both sudden and drawn out. On a geological timescale, they can occur quickly. On the ground, they may unfold as repeated local losses, one valley, one herd, one region at a time, until absence accumulates into finality. People living through the Younger Dryas and its aftermath may still know mammoths in one generation and know stories of mammoths in the next. Giant deer may vanish from one district while lingering farther east or north. A world can still seem populated by its old giants, even while those giants are already in retreat from history. And yet the disappearance of megafauna is not the only living drama of the Younger Dryas. Human communities are under pressure too, and unlike mammoths, they do not simply endure conditions passively. They alter routes, technologies, food choices, and social patterns. They retreat, expand, cluster, and improvise. The same climatic reversal that narrows the survival margins of great Ice Age animals also forces people into new relationships with place, risk, and one another. If the animals reveal the ecological cost of instability, humans reveal the cultural one. For human communities, the Younger Dryas is not an abstract climate event. It is a change in the terms of survival. People at the end of the Pleistocene are already masters of mobility, observation, and adaptation. They know how to follow herds, read weather, exploit seasonal abundance, and move across difficult country with a precision later sedentary societies often underestimate. But skill does not erase vulnerability. When climate shifts abruptly, the challenge is not simply colder air. It is that the world becomes less legible. Familiar patterns of animal movement, plant growth, water reliability, and seasonal timing begin to drift. Routes that made sense in one generation become riskier in the next. Camps that once stood near dependable resources may no longer hold the same value. The Younger Dryas forces people to live inside uncertainty with even less margin than before. Across much of the Northern Hemisphere, late Pleistocene humans are still living in relatively small groups, often highly mobile and tied closely to local ecologies. Their knowledge is intimate rather than generalized. They do not know climate in global terms, but they know where reindeer cross a valley in late autumn, which lakes keep fish under ice, where edible roots emerge first after snowmelt, where wood can still be found on open ground, where sheltering cliffs hold less wind in winter, where stone suitable for tools lies exposed, and where the land becomes dangerous after heavy thaw. When the Younger Dryas begins, this knowledge does not become useless, but some of it begins expiring faster. This is one of the most important human dimensions of abrupt climate change. People do not merely adapt to average conditions, they adapt to timing and predictability. A landscape can remain physically inhabitable while becoming strategically unreliable. If migratory animals alter their routes or density, a hunting system built on recurring seasonal concentration points becomes less dependable. If water sources behave differently under colder or drier conditions, old camp locations may no longer be worth the risk. If plant productivity declines or becomes more variable, communities may need to broaden diets, move more often, or intensify storage where possible. The record rarely preserves these decisions directly, yet archaeology often catches their shadows in changing settlement patterns, shifting toolkits, and altered use of space. In Europe, the Younger Dryas appears to coincide with reorganization in human settlement and subsistence strategies in several regions. As colder, more open conditions return, some communities appear to track the ecological changes by moving with prey and favoring landscapes suited to cold-adapted animals once again. Open country hunting remains important, but the precise regional picture varies depending on what the environment is doing locally. Some valleys that had begun transitioning toward more wooded or wet conditions may once again favor broader visibility and movement. Other areas become harsher or less reliable overall. Scholars still debate the relative importance of climate versus social factors in many archaeological transitions, and the evidence remains incomplete because preservation is uneven. But there is little doubt that human groups are responding actively to the return of cold. Technology becomes part of that response, though often in subtle ways rather than through any sudden invention that transforms everything at once. Toolkits shift according to prey, mobility needs, available raw materials, and the demands of different seasons. Hunting strategies may become more focused or more flexible, depending on what animals remain abundant. Clothing, shelter design, fuel use, and mobility planning all matter immensely, though these often survive archaeologically only in fragments. A sharpened point, a scraper, a pattern of hearths, a scatter of animal bone, the location of a campsite relative to water and sheltering terrain, these are the traces from which whole adaptive systems must be inferred. The silent reality behind them is that colder worlds are labor-intensive. Every degree of climatic deterioration multiplies the cost of staying alive. One lesser-known difficulty is fuel. In open late Pleistocene environments, wood can be scarce, especially in cold regions where forest cover is limited. People may rely on driftwood, shrubs, peat in some later settings, or even animal dung where available, but the availability and transport of fuel shape where winter occupation is possible, a colder, windier. Younger Dryas landscape is not simply a harder hunting ground, it is also a harder heating problem. Camps cannot be placed anywhere. They must balance shelter, water, prey access, raw materials, and fuel. A climate reversal changes that equation constantly. In the Near East, the human stakes may be even more historically consequential. During the warmer Berling-Alarud interval, parts of the Levant support increasingly rich exploitation of wild cereals, nuts, small game, and other resources by communities often associated with the Natufian tradition. Some settlements become more substantial and more repeatedly occupied than many earlier hunter-gatherer sites. This does not mean a simple march toward farming, and scholars still debate the exact degree of sedentism and variability among different Natufian groups. But it does suggest that in some especially productive ecologies, people are able to stay longer, invest more in place, and build lifeways that are less purely mobile than before. Then the Younger Dryas changes the background conditions. Cooler, drier climate in parts of Southwest Asia may reduce the reliability of wild plant stands and local water resources. If rainfall declines or becomes more erratic, landscapes supporting dense, predictable patches of useful plants become less dependable. Communities that had begun leaning into local abundance may face a difficult choice: move more, intensify collection and storage, broaden subsistence, or begin exerting more deliberate control over favoured species. This is where some of the most influential debates in archaeology begin. Did the Younger Dryas help push certain human groups toward cultivation by making wild resources less secure? Did climate stress encourage experimentation with planting, tending, and storage? Or were such developments already underway for social and ecological reasons that cannot be reduced to hardship alone? No single explanation fully accounts for the origins of agriculture, and most scholars are cautious about portraying the Younger Dryas as a single trigger. Human societies do not transform their food systems because climate issues an order. Social traditions, knowledge systems, local ecologies, demography, mobility choices, and sheer contingency all matter. Still, the Younger Dryas seems to intensify the pressures under which experimentation becomes useful. If resources once gathered opportunistically begin fluctuating more sharply, then investing labour in favoured plants may become a more attractive gamble. If communities are already somewhat tethered to productive zones, then mobility is no longer the only or easiest solution to hardship. In that sense, the climate reversal may not invent agriculture, but it may sharpen the conditions under which proto-agricultural behaviours gain value. Beyond the Near East, the human response is equally real even where it leaves less famous historical legacy. In the Americas, people living through the Younger Dryas face a continent still adjusting to retreating ice, changing hydrology, and shifting ecological opportunities. Coastal zones are being drowned by rising seas, erasing many traces of early settlement from the modern landscape. Interior routes open and close in response to ice retreat, vegetation change, and water availability. Big game hunting remains important in some areas, but the broader picture may already be diversifying as communities exploit fish, birds, small mammals, plant foods, and regionally specific resources. The end of the Clovis horizon roughly overlaps with the Younger Dryas onset, but that overlap should not be forced into a single dramatic explanation. More likely it reflects human adaptation to a world whose conditions are becoming regionally varied and increasingly unstable. Mobility itself changes meaning under these conditions. In a more generous warming landscape, movement can be expansionary, exploratory, opportunistic. Under Younger Dryas stress, movement may become defensive. Groups relocate not simply because new territory beckons, but because old territory no longer performs as expected. Seasonal rounds may lengthen or contract depending on prey distribution and water reliability. Social networks become more important when local failures must be buffered through exchange, marriage ties, information sharing, or access to distant resources. Archaeology rarely preserves these social strategies directly, but the distribution of exotic stone, repeated use of certain aggregation sites, and shifts in regional settlement density hint at how important intergroup links may have been. Another quiet but important consequence is time depth of memory. Human communities carry environmental knowledge across generations through practice, place attachment, and oral transmission. Abrupt climate change places stress on inherited knowledge because it changes the reliability of learned expectations. A grandparent's advice about when fish run, where game shelters in winter, or which valley stays productive through dry months may still hold partly true, but less fully than before. That does not mean cultural knowledge fails, it means it must adapt faster. Societies that can revise expectations, diversify risk, and maintain wider informational networks may cope better than those too tightly specialized on vanished conditions. Children born during the Younger Dryas grow up in a world already shaped by the cold. For them, the harsher climate is not reversal but normality. That fact matters because adaptation is not only technological, it is developmental. People learn the world they inherit. 1,000-year climatic downturn is long enough for lifeways to be rebuilt around it. Hunting knowledge, mobility patterns, seasonal scheduling, and even symbolic relationships to animals and landscapes may all shift under conditions that no one alive remembers beginning. Abrupt onset matters most to the first generations. Duration reshapes everyone after. Yet even amid hardship, human adaptability remains extraordinary. Communities do not simply endure the Younger Dryas passively. They respond with flexibility, regional specialization, intensified knowledge of local ecologies, and perhaps in some places with the earliest steps toward new forms of plant management. Climate stress narrows options, but it can also expose possibilities. A stand of wild grain once casually harvested becomes worth watching more carefully. A productive wetland becomes a place to return to with greater regularity. Storage becomes more valuable when seasonality sharpens. Social alliances become more useful when local environments fluctuate. Out of instability, new cultural strategies begin to harden into tradition. This is why the human story of the Younger Dryas is so significant. It is not a tale of simple victimhood. It is a tale of pressure meeting ingenuity. But ingenuity does not erase cost. People likely abandon places they had begun to know deeply. They face failed expectations, lean years, and narrower ecological margins. They watch animals shift, wetlands shrink or freeze longer, and useful plants behave differently. They enter a world in which adaptation is still possible, but ease is gone. And nowhere is that tension between hardship and innovation more visible than in the Natufian world of the Levant, where communities already living closer to place than many earlier foragers find themselves confronting a colder, drier interval at precisely the moment when later history begins to take shape. If the Younger Dryas leaves one of its deepest human fingerprints anywhere, it may be there, in the uneasy boundary between foraging abundance and the first serious steps toward cultivation. In the Levant, the Younger Dryas enters a landscape already carrying the faint outline of a different human future. This is one of the reasons the region matters so much in the larger story. Elsewhere, the climate reversal disrupts hunting ranges, migration routes, and local ecologies in ways that are profound but difficult to connect directly to later world history. In the Near East, by contrast, the disturbance arrives in places where some communities are already beginning to live with unusual intensity in relation to particular landscapes. The Natufian world is not yet agricultural in the full sense, not yet a civilization of planted fields, domesticated herds, and permanent villages spread across a settled countryside. But it is also no longer simply the world of highly mobile foragers moving lightly across broad territories. In certain zones, people are staying longer, building more substantial structures, gathering abundant wild cereals, processing plants intensively, and investing in specific places with a depth that hints at what will come later. That hint is what makes the Younger Dryas here feel so consequential. During the preceding warmer interval, parts of the Levant offer a productive patchwork of woodland, steppe, wetland, and grassland ecologies. Wild stands of cereals such as barley and wheat grow in favourable areas. Gazelle remain important prey, but people also exploit small game, birds, fish in some settings, nuts, legumes, tubers, and a broad spectrum of local resources. Some Natufian sites contain semi-subterranean stone-built houses, storage features or possible storage behaviours, grinding stones for processing plants, and signs of repeated occupation over long periods. This does not mean every Natufian group is sedentary in the same way. Scholars still debate the balance between mobility and permanence across the culture, and regional variability is substantial. But there is no question that some communities are living in a more anchored relationship to place than many of their predecessors. Anchoring changes the meaning of climate stress. A highly mobile foraging group can respond to deteriorating local conditions by moving, though movement always has costs. A community more invested in a particular ecological zone faces a harder decision. If the local stands of wild cereals become less reliable because of cooler, drier, Younger Dryas conditions, leaving may mean abandoning built places, familiar collection grounds, nearby water sources, burial landscapes, and social ties embedded in a known territory. Staying, on the other hand, means finding ways to extract more dependable returns from a less dependable environment. The tension between those choices may be one of the most important human consequences of the Younger Dryas anywhere in the world. Evidence from the region suggests that the climatic reversal likely brings cooler and drier conditions to at least parts of the Levant. Though the exact severity and local expression vary from place to place, rainfall patterns in this region are extraordinarily important because they govern the productivity of the so-called wild cereal zone and shape the difference between landscapes that can support dense and repeated human use and those that cannot. A modest decline in effective moisture can shift the abundance, distribution, and predictability of useful plants. Wild stands may become patchier, yields may fluctuate more, the seasonal rhythm on which gathering depends may become less secure. What survives in the record suggests that some Natufian communities respond not with a single uniform strategy, but with a range of adaptations that include renewed mobility in some cases and intensified local exploitation in others. This is where archaeology becomes especially careful, because later developments tempt people into telling too neat a story. It is attractive to imagine the Younger Dryas as the crisis that forces humans to invent agriculture, as though one bad climatic turn drives hungry foragers straight into farming. Reality is more tangled. Agriculture is not a single invention that appears fully formed under duress. It emerges gradually, unevenly, and through repeated experimentation with plants, seasons, storage, labour, and landscape management. People already know these plants intimately. They already harvest them, process them, perhaps encourage them in subtle ways. The line between foraging and cultivation is not a cliff, it is a long slope. The Younger Dryas may steepen that slope, but it does not create the terrain from nothing. Grinding stones found at Natufian sites are a good example of this pre-existing intimacy. These are not casual tools. Repeated use polishes them, and plant residues sometimes survive to hint at what was processed there. Gathering wild cereals in quantity requires skill, timing, and labour. Processing them requires investment. That investment makes sense in landscapes where plant abundance is predictable enough to reward repeated return. If Younger Dryas drying or cooling begins undermining that predictability, then people who are already committed to exploiting these resources face a choice: diversify away from them, move more, or intervene more directly in how those plants are accessed and perhaps maintained. Scholars still debate the relative weight of these responses, but it is precisely this tension that makes the period so important. One lesser-known aspect of the Natufian story is how much it is also about storage and scheduling, rather than simply about food production. Wild cereals ripen seasonally and must be collected in a narrow window. If people want to rely on them more heavily, they need ways to process, preserve, and protect those harvests. Storage is a strategy for dealing with uncertainty. It allows a community to survive lean seasons, failed hunts, and climatic variability with something more than hope. In that sense, the Younger Dryas may encourage not only the tending of plants, but the social importance of delayed return economies gathering now to survive later, investing labour today against a harsher tomorrow. Once that logic strengthens, a different relationship to time enters human subsistence. At the same time, not all Natufian communities respond by becoming more settled. Some archaeological evidence suggests increased mobility or reorganization in parts of the Levant during the Younger Dryas. This matters because it warns against a teleological reading. Climate stress does not push everyone in the same direction. In some environments, staying put becomes too costly. In others, concentrated resources still reward place-based life. Human societies are not passive instruments reacting mechanically to weather. They are social systems making choices within constraints, and those choices are shaped by tradition, risk tolerance, demography, and local opportunity. The evidence remains incomplete, but what survives suggests a mosaic of responses rather than one simple pathway. Still, the long-term implications are hard to ignore. Shortly after the Younger Dryas ends and the Holocene begins, the archaeological record in Southwest Asia starts showing stronger evidence for early cultivation, domestication processes, and more fully settled village life in some areas. That does not prove the Younger Dryas caused agriculture, but it does suggest that this cold interval may have acted as a crucible, a period in which communities tested behaviours that later became foundational, tending productive patches, scheduling harvests more carefully, storing food, living more permanently near favoured resources, and perhaps exerting selective pressure on plants through repeated harvesting and sowing-like disturbance. These are not yet full agriculture, but they move in its direction. Stress does not invent ideas, but it can decide which ideas become worth keeping. The social dimension may be just as important as the ecological one. Natufian communities are not only gathering food, they are burying their dead, marking places with memory, and developing more persistent ties to landscape. Cemeteries, architecture, and repeated occupation all suggest that territory is no longer merely traversed. It is inhabited in a deeper sense. That can make mobility harder, not physically but culturally. Abandoning a place where ancestors are buried is not the same as leaving an ordinary seasonal camp. Under climatic deterioration, such attachments may generate pressure to remain and intensify local resource use rather than simply move on. In this sense, the Younger Dryas may interact with identity as much as subsistence. Gazelle hunting adds another layer. In much of the Natufian world, gazelle remain a crucial resource, and zooarchaeological evidence sometimes suggests shifts in hunting intensity, prey structure, and demographic patterns that may reflect growing human pressure on local animal populations. If climate stress reduces the reliability of plant resources while human communities remain concentrated, hunting pressure can intensify. That in turn may make wild plant exploitation even more important, creating a feedback toward broader spectrum subsistence and perhaps toward increased management of favored species. No single explanation fully accounts for the balance between hunting, gathering, storage, and cultivation, but the whole system seems to tighten under Younger Dryas conditions. There is also the matter of children and labour. Cultivation, even in its earliest experimental forms, changes who works, when they work, and how communities organise seasonal effort. Harvesting wild cereals at scale, processing them, protecting stores, and perhaps returning deliberately to favourable stands all require coordination. This is not simply a technological shift, it is a social one. The Younger Dryas may not only make certain foods more valuable, it may make cooperation around those foods more central to community life. If so, the interval's legacy is not only agricultural but organisational. People begin living on more scheduled terms. And yet caution remains essential. Scholars still debate how direct the link is between Younger Dryas stress and the emergence of agriculture. Some emphasise that cultivation begins in some form only after the climatic reversal ends, suggesting that the more stable early Holocene, rather than the Younger Dryas itself, provides the real opening for domestication. Others argue that the stress of the Younger Dryas lays the groundwork by making experimentation necessary, even if the eventual payoff comes under later stability. Both views may contain part of the truth. Hard times often produce innovations that only flourish once conditions improve. The cold interval may force the question, while the Holocene permits the answer. What seems safest to say is that the Younger Dryas sharpens an existing human problem in the Levant: how to live when a productive landscape becomes less trustworthy, but remains too valuable, too familiar, and too socially meaningful to abandon easily. That problem does not create agriculture in a single stroke. It creates pressure towards strategies that narrow the distance between foraging and farming. The Natufian world becomes a turning point not because it crosses the line cleanly, but because it lingers on it under stress. In that sense, the Younger Dryas in the Levant is about more than cold. It is about hesitation at the threshold of a new human way of life. Communities already leaning toward greater permanence are forced to confront scarcity, unpredictability, and local attachment all at once. Some move, some endure, some intensify what they already know. Some begin testing the logic of delayed return more rigorously than before. Out of that uneasy period comes not a sudden revolution, but a set of habits and pressures that later become world-changing. And while the Levant often receives the most attention because of its connection to agriculture, it is only one part of the broader map. The Younger Dryas does not fall evenly across the planet, and neither do its consequences. Europe, Southwest Asia, and the Americas each experience the reversal through different ecologies, different human traditions, and different risks. To understand the event fully, the lens has to widen again. The Younger Dryas is often described as though it were a single experience shared by the world at once, a sudden freezing that descends evenly across the planet. That is useful for headlines, but not for understanding. The event is real precisely because so many different records preserve it. Yet the farther one moves from Greenland and the North Atlantic, the more its expression begins to vary. In one place the central story is brutal cooling, in another it is drying. Somewhere else it is a change in storm tracks, a weakened monsoon, a shortened growing season, a rearranged coastline, a delayed thaw, or an ecological mosaic turned less predictable. The Younger Dryas is global in significance, but regional in texture. To follow it across continents is to watch one climatic disturbance become many lived worlds. Europe offers one of the clearest pictures of the cold itself. Much of the continent has already begun adjusting to the earlier post-glacial warming, with shrubs and pioneer woodland pushing into some areas, wetlands spreading in others, and animals redistributing themselves across a changing mosaic. Then the Younger Dryas interrupts that recovery. In northern and central Europe, pollen records show a retreat or stalling of woodland expansion and a renewed prominence of cold-adapted herbs and shrubs. In some mountain systems, glaciers or snowfields stabilize or re-advance. Beetle remains indicate colder conditions, and loess activity reflects greater aridity and exposed sediment in suitable regions. The continent does not become uniformly uninhabitable, but it becomes harder, more open in some places, more dust-prone, and more constrained by seasonality. For people in Europe, this means landscapes that had briefly begun to diversify ecologically now tilt back toward conditions favoring mobility and cold-adapted prey. Reindeer remain critical in many regions. Open country hunting continues to shape lifeways. Yet Europe is not one environment. Atlantic zones, continental interiors, uplands, and river valleys each respond differently. Some areas remain productive enough to support repeated occupation, while others become more marginal. The archaeological record suggests adjustment rather than simple collapse. Human groups shift settlement patterns, exploit changing ecotones, and continue adapting to a world that insists on rewriting its own geography. The evidence remains incomplete because many sites are poorly preserved or unevenly dated, but it is clear that Europe lives the Younger Dryas as a return to harsher northern realities without becoming a simple replay of the old glacial age. Southwest Asia lives the event differently. Here the question is less often one of ice and more one of water. The Levant, Upper Mesopotamian margins, and surrounding regions occupy a precarious ecological position even in relatively favourable times. Productive zones are often narrow, rainfall sensitive, and deeply dependent on the balance between Mediterranean moisture, local topography, and seasonal timing. When the Younger Dryas shifts that balance toward cooler and drier conditions in parts of the region, the consequences are immediate. Wild cereal stands may become less reliable. Water availability changes. Grasslands and woodlands contract or reorganize. Human communities already leaning more heavily on local abundance must decide whether to move, intensify, diversify, or endure. In this part of the world, the climatic reversal feels less like a dramatic freeze than like the tightening of scarcity. Farther east across Eurasia, the story grows more complex. Steppe, forest steppe, tundra, and mountain systems each respond according to their own geography and climatic sensitivity. In some areas, cold-adapted open landscapes persist longer. In others, changing moisture balance may matter more than raw temperature. The Great Northern Plains and continental interiors do not all react in lockstep, and chronology becomes more difficult as records grow patchier. Scholars still debate how sharply some Siberian and Central Asian regions register the Younger Dryas compared with the North Atlantic core, but the broader late Pleistocene picture remains one of unstable transitions. Large animals, mobile human groups, thawing and refreezing ecologies, and shifting hydrology all continue interacting in a world not yet committed to the stable Holocene that will follow. The Americas present an even more varied map. North America in particular is still dominated by deglaciation itself. The Laurentide ice sheet remains an enormous force, shaping drainage, wind patterns, temperature gradients, and access routes across the continent. The Younger Dryas unfolds here not against a settled background, but within an already unstable geography of retreating ice, enormous proglacial lakes, changing rivers, and rising seas. In eastern and central North America, pollen records and lake sediments show significant ecological change associated with the interval. Forest distribution shift. In some regions, colder conditions delay the northward advance of tree species or reorganize the composition of plant communities. In others, hydrological changes become central. The continent does not experience one uniform climate response because its own geography is still being rebuilt as the event unfolds. In the American West, lake levels, wetland distributions, and local temperature-moisture balances create regionally distinct stories. Some basins preserve evidence for changing effective moisture rather than dramatic simple cooling. High elevations may respond differently from lowland deserts or grasslands. Coastal regions are further complicated by sea level rise, which continues erasing or drowning evidence of late Pleistocene occupation. It is entirely possible that some of the most important human responses to Younger Dryas conditions along ancient shorelines are now underwater and largely lost to archaeology. What survives on land may therefore give only a partial view of how communities adapted to this fluctuating continent. The overlap between the Younger Dryas and the end of the Clovis archaeological horizon in North America has attracted enormous attention, often far more than it can comfortably bear. Clovis technology, with its distinctive fluted projectile points, appears within a relatively narrow time frame and then gives way to more regionally varied traditions. The coincidence with climatic reversal has tempted many into simple explanations, whether via impact theory, ecological collapse, or cultural replacement, yet the safest reading is more nuanced: a rapidly changing climate, retreating ice, shifting prey distributions, extinctions of some large mammals, and the increasing regionalization of human adaptation all likely contribute to the transition. The end of Clovis is not necessarily the end of a people, but the end of a particular widespread technological pattern in a continent becoming less uniform and more ecologically diverse. South America is less often centered in popular discussions of the Younger Dryas, but that does not mean it stands untouched. The Southern Hemisphere does not mirror the Northern Hemisphere in a simple, synchronized way, and this is one of the reasons the Younger Dryas remains so scientifically interesting. Some Southern records show climatic shifts that may correspond broadly to the event or to related reorganizations in hemispheric heat balance, but their timing and magnitude do not always align neatly with the Northern pattern. This asymmetry is exactly what one would expect if ocean circulation changes in the North Atlantic help drive the event. Cooling concentrated in the north can be associated with more complicated, sometimes opposite or delayed responses elsewhere. The disturbed planet redistributes its imbalance unevenly. That hemispheric contrast matters because it prevents the Younger Dryas from being reduced to a fairy tale freeze. If the climate system is reorganized through ocean circulation, the consequences must ripple through the whole coupled Earth system, but not identically in every basin or hemisphere. Some tropical rainfall belts may shift southward or northward. Some southern hemisphere regions may experience hydroclimatic changes rather than dramatic cold. Antarctic records and Southern Ocean data contribute to this bigger picture, though aligning them precisely with northern chronologies remains challenging. The world is connected, but not synchronized like a machine. There are also drowned worlds on this map, and they may be some of the most important ones. During the Younger Dryas, sea level is still rising overall, as ice sheets continue melting on long timescales despite the cold reversal. That means vast coastal plains that had supported human and animal life during earlier phases of the late Pleistocene are progressively lost to the sea. The North Sea basin, now submerged, once contains habitable landscapes often referred to as Doggerland in later discussions. Continental shelves elsewhere around the globe preserve the ghost geography of campsites, river mouths, lagoons, marshes, and migration corridors now underwater. These lost coasts complicate every continental comparison. We are comparing regions partly through the evidence left on land. While some of the best land from a human perspective no longer exists above sea level. This is one of the strangest features of the terminal Pleistocene world. The map people live on is not the map available to archaeologists. Shores are farther out, islands are joined to mainlands, estuaries sit in different places, river valleys extend across areas now flooded. When the Younger Dryas alters climate, it does so across a geography only partly recoverable today. Human responses in these coastal environments may have been substantial, especially where marine, estuarine, and wetland resources buffered inland climatic deterioration. But because rising seas erase so much of that evidence, the surviving record is skewed inland toward caves, uplands, preserved lake margins, and other places lucky enough to endure. Regional comparison therefore reveals two truths at once. First, the Younger Dryas is undeniably a major climatic event of broad significance. Second, no continent experiences it in exactly the same way. Europe feels the return of near-glacial cold most strongly. Southwest Asia feels tightening water stress and subsistence pressure. North America experiences the reversal inside the chaos of deglaciation and megafaunal turnover. Tropical and southern hemisphere regions register more complex atmospheric and hydrological consequences. Coastal worlds, some now drowned, likely provide further stories we can only partly reconstruct. This unevenness is not a weakness in the Younger Dryas case. It is part of what makes the event intelligible. If the cause lies in ocean circulation, freshwater forcing, sea ice, and atmospheric feedbacks, then different regions should indeed record different consequences. A world system perturbed in one critical zone does not send out identical copies of the same weather. It sends altered gradients, redirected moisture, expanding ice in some places, drought in others, and delayed ecological transitions across wide areas. The event's regional variety is therefore one of the strongest reasons to treat it as a true reorganization rather than a mere local anomaly. And yet, after roughly 12 centuries of this disturbed order, the Younger Dryas ends as abruptly as it began. The cold that had settled in as a new normal does not simply fade by degrees into the Holocene. Once again, the system seems to cross a threshold. The North Atlantic warms, ice core signals jump, vegetation advances. A world that had spent generations under renewed climatic strain suddenly moves into the warmer stability that will cradle all later civilization. The deep chill finally breaks. When the end comes, it does not arrive as a slow and reassuring release. The Younger Dryas begins abruptly, and in the records that matter most, it ends the same way. After roughly 1,200 years of renewed cold, disrupted rainfall, altered winds, expanded sea ice, and ecological strain. The climate system appears to shift again with startling speed. In Greenland ice cores, the signal is dramatic. Oxygen isotope values rise sharply, indicating rapid warming. Dust concentrations fall. Atmospheric conditions reorganize. The long interruption that had held the world between Ice Age and Holocene suddenly gives way. The deep chill breaks, and the planet moves into the warmer, more stable interval that will define the rest of human history up to the present day. This abrupt ending is one of the most unsettling features of the entire Younger Dryas story. If the cold had faded gradually over centuries, it might seem like a standard climatic oscillation, severe but unsurprising. Instead, the records suggest threshold behavior once again. The system does not merely drift out of the Younger Dryas, it tips out. Whatever combination of weakened ocean circulation, freshwater forcing, sea ice expansion, and atmospheric feedbacks had maintained the cold state appears to lose its grip. Warmth returns rapidly to the North Atlantic region. Conditions that had constrained ecosystems and human communities for generations begin changing within spans short enough to be felt inside human lifetimes. The evidence remains incomplete in all the usual ways, and local responses vary, but the broader transition is unmistakable. The world reopens. For Greenland, this reopening is especially clear because the ice preserves change at such high resolution. Annual layers capture the shift not as a vague trend, but as a sharp upward jump in temperature proxies. The precise number of years over which the warming occurs has been debated, and scientists remain careful about the temptation to oversimplify a complex process. But in paleoclimatic terms, the transition is astonishingly fast. It is one more lesson in how abruptly the climate system can reorganize once key controls move past a threshold. The Younger Dryas had already shown that warming could be interrupted by sudden cold. Its end shows the reverse. A climate state that has lasted more than a millennium can still collapse quickly. This matters because the end is not merely relief, it is another disruption. Ecosystems that have spent centuries adjusting to Younger Dryas conditions now have to adjust again, this time to warmer temperatures, retreating sea ice, changing precipitation, and a resumed northward advance of vegetation zones. Forests begin spreading into areas where tundra and open herb communities had persisted. Wetlands shift. River regimes alter with different snowmelt timing and hydrology. Animals adapted to open, cold landscapes face renewed contraction of their preferred habitats. Human communities built around Younger Dryas conditions now face a different map of opportunity and risk. The end of the cold is beneficial in many broad ways, but transitions are rarely gentle for those inside them. The ocean likely sits at the center of this reversal, just as it does in the onset. If the Younger Dryas is maintained by a weakened Atlantic overturning circulation combined with sea ice feedbacks, then its end implies that overturning strengthens again. That could happen because freshwater forcing declines, because meltwater routing changes, because sea ice retreats enough to alter feedback loops, or because the system simply crosses back over a stability threshold once the balance shifts far enough. Here again, no single explanation fully accounts for every detail. Scholars still debate the exact sequence by which deep water formation intensifies and how rapidly the ocean atmosphere system responds. But the broad logic is persuasive. The northward transport of heat resumes strongly enough to reorganize the climate of the North Atlantic and beyond. Sea ice retreat is a crucial part of this story. During the Younger Dryas, expanded sea ice helps maintain cold conditions by reflecting sunlight and insulating the ocean from the atmosphere. Once warming begins, shrinking sea ice reverses those effects. More ocean surface is exposed, more heat can move from water to air. More solar energy is absorbed by darker open water. The new state reinforces itself just as the old one had. This is one of the most important features of abrupt climate change. Feedbacks do not care whether they are producing cold or warmth. Once a new trajectory takes hold, it can accelerate the shift. Vegetation responds with a speed that is impressive by ecological standards, though of course slower than a change in air temperature. Pollen records across Europe show the renewed expansion of trees and temperate or boreal plant communities into regions where cold-adapted herbs and shrubs had dominated during the Younger Dryas. Birch and pine advance, woodland edges move. In some places, soil development accelerates under warmer and wetter conditions. Lakes change their chemistry and productivity as catchments become more vegetated and seasonality softens. The visual world would have altered over generations: more cover, more wood, more insects in warm months, different animal tracks, new kinds of fuel, and different constraints on movement. A person living long enough across the transition might watch familiar open country begin closing again. For cold-adapted megafauna, this renewed warming is devastating in the long term. If the Younger Dryas has offered some populations a temporary extension of suitable habitat, the end of the interval removes that reprieve. Forest and wetland expansion reduce open forage landscapes in many regions. Plant communities change in ways that favour smaller-bodied and more temperate-adapted animals. The ecological order of the mammoth steppe continues breaking apart. Surviving Ice Age giants are pushed into smaller refuges or disappear altogether. This is why the Younger Dryas can seem paradoxical in extinction history. It is both a stress event in its own right and, for some species, a last pause before final Holocene habitat loss resumes. The ending of the cold does not rescue the old fauna, it closes the book on them more decisively. For human communities, the consequences are more mixed and ultimately more transformative. Warmer and more stable, Holocene conditions support increased plant productivity in many regions, more predictable seasonality, and the spread of ecological zones that can sustain denser, more settled populations. That does not mean life suddenly becomes easy. Forests can make hunting more difficult in some ways than open country. New diseases, new insects, and new competition emerge in warmer environments. But compared with the sharp instability of the Younger Dryas, the early Holocene offers something extraordinarily valuable: reliability. Seasons become more dependable. Resource distributions become easier to learn and exploit over the long term. In landscapes like the Levant, this reliability may be exactly what allows experimental cultivation and more permanent settlement to take firmer hold. One lesser-known aspect of the Younger Dryas termination is how important chronology becomes here for understanding human history. The warming at the onset of the Holocene aligns broadly with major cultural transitions in several regions, including the emergence of pre-pottery Neolithic communities in Southwest Asia soon afterward. Scholars debate causation, as they should, but the timing is suggestive. Hard conditions may sharpen experimentation, while stable conditions allow successful experiments to spread. The Younger Dryas may therefore function as a kind of testing ground, and the Holocene as the interval in which tested strategies become scalable. This would help explain why agriculture is not born fully during the cold phase itself, but blossoms in the warmer world that follows. The atmosphere also changes in ways that ripple far from the North Atlantic. Dust decreases in Greenland, rainfall belts shift again, monsoon systems adjust to the new distribution of heat between ocean and land. Lakes in some regions refill or stabilize under altered hydrological regimes. In others, warming opens the way to stronger evaporation and different moisture balances. As always, the planet does not respond uniformly, but the overall tone changes. The Younger Dryas is a world of tension, brittle edges, and defensive adaptation. The Holocene begins as a world where cumulative growth becomes easier, where ecosystems spread rather than merely endure, and where human communities can begin investing in landscape with a new confidence. That confidence should not be mistaken for permanence. The early Holocene still contains climatic fluctuations, local crises, floods, droughts, and regional instability. Yet compared with the terminal Pleistocene, it is remarkably steady. This steadiness may be one of the most underappreciated facts in human history. Agriculture, villages, cities, writing, kingdoms, empires, and industrial civilization all emerge not merely because humans are inventive, but because they do their inventing within an unusually stable climatic interval. The end of the Younger Dryas marks the opening of that interval. Without it, later history might look radically different, if it happened at all in the form we know. There is also an emotional strangeness to the transition. For generations, people have adapted to a colder, more demanding world. Those born near the end of the Younger Dryas may grow old in a warming landscape that feels increasingly unlike the one they learned in childhood. Roots shift, resources change, animals withdraw or reappear in different combinations. Plants advance into ground once too harsh for them. The world once again asks for revised knowledge. Human adaptability is equal to the task, but adaptation is never free. It means letting old expectations die and building new ones from experience. This is one reason the Younger Dryas matters as more than a scientific puzzle. It is a reminder that climate stability is not the natural baseline against which all else should be measured. It is a condition that can arrive suddenly, just as instability can. The people entering the Holocene do not know they are stepping into the climatic shelter in which civilization will one day grow. They only know that the cold is relenting, that the world is becoming more generous in certain ways, and that possibilities closed off for many generations are opening again. So the end of the Younger Dryas is not simply the conclusion of a cold phase, it is the unlocking of a planetary mood. The ice has not vanished overnight. The seas are still rising. The old giants of the Pleistocene are still fading, but the grip of abrupt late glacial instability loosens, and in its place comes the long, relatively calm interval that humans will later mistake for normal. The strange chill that had delayed the future finally releases it. For modern climate science, the Younger Dryas is not merely a fascinating prehistoric episode. It is a warning preserved in deep time. Its details belong to a world of retreating ice sheets, mammoths, drowned plains, and foragers living at the edge of seasonal uncertainty. But its deeper lesson reaches directly into the present. Climate systems do not always change in slow, smooth, easily anticipated ways. They can cross thresholds. They can reorganize abruptly. They can remain apparently stable while hidden pressures accumulate, and then move quickly into a different state once certain balances are disturbed. The Younger Dryas is one of the clearest ancient examples of that behavior, and that is why scientists continue returning to it with such urgency. The most obvious connection lies in the Atlantic. The leading explanation for the Younger Dryas centers on disruption of the Atlantic meridional overturning circulation, the broad system that today still helps carry warmth northward through the ocean. It is not identical in every detail to the circulation patterns of the terminal Pleistocene, because the planet itself is different now. Ice sheets are far smaller. Coastlines have changed. Background climate conditions are warmer. But the principle remains deeply relevant. Ocean circulation depends on density contrasts shaped by temperature and salinity, large freshwater inputs, shifting wind patterns, and feedbacks involving sea ice can all affect how the system behaves. The Younger Dryas shows that when such a system is pushed hard enough, the consequences can be large and abrupt. This does not mean the present is about to replay the Younger Dryas in exact form. Scientists are careful about that, and rightly so. The modern climate is warming because greenhouse gas concentrations are rising rapidly due to human activity. The Younger Dryas, by contrast, unfolds during deglaciation under very different background conditions. No single explanation fully accounts for the precise comparison between then and now, and careless analogies can mislead. Yet differences do not erase relevance. What the Younger Dryas demonstrates is that ocean atmosphere systems can possess tipping behaviour, and tipping behaviour remains one of the central concerns of contemporary climate research. Among the most widely discussed questions today is whether the modern overturning circulation in the Atlantic could weaken significantly under continued warming and enhanced freshwater input from melting Greenland ice, increased precipitation, and changing runoff. Observations and models suggest that this circulation may already be weakening relative to earlier periods, though the exact magnitude, causes, and long-term implications remain debated. That debate itself reflects the caution scientists have learned from studying past abrupt changes. Large systems are noisy, direct observation is limited, models differ, yet the possibility of substantial weakening is taken seriously, not because scientists enjoy drama, but because the paleoclimate record shows that dramatic reorganizations have happened before. If such weakening were to continue, the consequences would not be simple or evenly distributed. Parts of the North Atlantic region could warm less than the global average, or even experience relative regional cooling compared with a broader warming trend. Rainfall belts could shift, storm tracks might change, marine ecosystems could be affected. Sea level along some coasts could rise differently because of changes in ocean dynamics. Tropical rainfall systems and monsoons might also respond as the redistribution of heat between hemispheres changes. In other words, the lesson of the Younger Dryas is not that one region freezes while the rest of the world waits unchanged. It is that a disturbance in a critical circulation system can spread through many linked parts of the climate. This is where modern misunderstanding often enters. People tend to imagine climate change as a uniform raising of temperatures, as though the whole planet were a single room with a single thermostat. The Younger Dryas reminds us that climate is a network of moving parts. Warming overall can coexist with regional cooling, drying, flooding, or circulation change. A planet gaining heat can still produce local surprises if the pathways moving the heat around begin to alter. That complexity does not weaken the case for present-day warming. It strengthens the case for taking Earth system instability seriously. The Younger Dryas also matters because it reveals the difference between forcing and response. A relatively modest push, if directed at the right threshold, can produce outsized effects. Freshwater entering a sensitive region of the North Atlantic does not need to cool the whole planet directly by itself. It only needs to disrupt a mechanism already doing crucial work. Once that mechanism weakens, sea ice, winds, albedo, and atmospheric feedbacks can amplify the outcome. This logic has become central to the study of tipping points more generally, not only in ocean circulation but in ice sheets, ecosystems, and monsoon systems. The world does not always respond proportionally. It responds through thresholds. One lesser known but important lesson from the Younger Dryas is methodological. It teaches scientists humility about timelines. If a climate transition happens over decades rather than millennia, then human institutions may be forced to confront changes faster than traditional historical intuition expects. The Younger Dryas onset is rapid enough to fit inside cultural memory if a society were large and literate enough to record it. The fact that it occurs before writing does not make it less real. It means only that the Earth recorded it instead of humans. Today, with instruments and satellites, people can watch change unfold in real time, but the speed problem remains. Systems can move faster than habits of planning, infrastructure, and politics are prepared to manage. This ancient event also widens the lens on what abrupt really means. Abrupt does not have to mean a single catastrophic instant. It can mean a sequence of bad decades that adds up to a radically different baseline by the end of one human life. That is, in some ways, more troubling than pure catastrophe. A meteor strike leaves no ambiguity. A circulation shift, rainfall drift, or ecological reorganization unfolds through accumulated consequences, each survivable alone, devastating in combination. The Younger Dryas is full of that pattern. Colder conditions, changing precipitation, dustier air, altered migration routes, shifting vegetation, ecological fragmentation, and cultural stress do not need to arrive with theatrical spectacle to alter the course of the world. For archaeologists and environmental historians, the event also sharpens a broader truth. Many major transitions in human life happen not simply because people invent new things, but because climate either permits or constrains the spread of those inventions. The stable Holocene matters as much as any tool or crop because it provides the environmental continuity in which fields, villages, and long-term planning become more feasible. The Younger Dryas stands just before that stability, a reminder of how contingent it all is. Civilization emerges not on a timeless Earth, but in a fortunate climatic lull following an era that proves how unstable the system can be. Modern researchers therefore study the Younger Dryas not out of antiquarian curiosity, but because it offers one of the best natural experiments for abrupt change available in the geologic record. Climate models are tested against it. Ocean hypotheses are measured against it. Chronologies are refined in light of it. It is one of those rare ancient events that is both distant and intimately relevant. A vanished cold age that still influences how scientists think about risk today. Every new sediment core isotopic study, cave record, or model run adds another piece not just to the past, but to the logic by which the future is assessed. There is a psychological lesson here as well. Modern societies are built on assumptions of continuity. Seasons may vary, economies may fluctuate, storms may come and go, but the larger background is assumed to remain broadly legible. The Younger Dryas shows how dangerous that assumption can be. A stable pattern can be temporary. A transition thought to be underway can stall or reverse. A climate regime can become the wrong one within the span of a lifetime. That is not cause for fatalism. It is cause for seriousness. The ancient record does not tell people that the future is hopeless. It tells them that the future is not guaranteed to remain comfortably familiar. At the same time, the Younger Dryas should not be used lazily as a slogan. Its real value lies in nuance. It is not proof that every present-day climate fear will unfold exactly as imagined. It is not a magical template that can be laid directly over modern conditions. It is something both more modest and more profound evidence that Earth's climate system has modes of behavior more abrupt, more nonlinear, and more interconnected than ordinary intuition prefers. Once that is accepted, the burden of proof shifts. The question is no longer whether abrupt change is possible. It clearly is. The question becomes how close modern forcing may push certain systems toward comparable thresholds. And in that sense, the Younger Dryas still sits beside us. Not as a ghost demanding repetition, but as a memory embedded in ice and sediment, warning that the planet's calm intervals are not permanent entitlements. The same species that once endured its cold now runs industrial civilization under a warmer sky, melting ice again, altering ocean salinity again, and loading the atmosphere with greenhouse gases at a pace unmatched in the event's ancient story. The causes are different. The lesson about fragility is not. So when scientists return to the Younger Dryas, they're really asking two questions at once. What happened then? In that strange millennium when Earth seemed to freeze again? And what does that ancient instability say about a world now being changed by human hands? The first question belongs to prehistory. The second belongs unmistakably to the present, and neither can be answered responsibly without the other close by. For all the evidence gathered from ice, lakes, caves, oceans, dust, pollen, fire traces, and ancient bones, the Younger Dryas still resists a perfect explanation. That resistance is part of what keeps it alive in science. Some events become clearer with each new study until disagreement narrows into detail. The Younger Dryas has certainly become clearer in broad outline. Few now doubt that it is a real and major climatic reversal near the end of the last ice age. Few doubt that its strongest expression lies in the North Atlantic world. Few doubt that ocean circulation, freshwater forcing, sea ice, and atmospheric feedbacks are central to the story. And yet when the question becomes more exact, what precisely started it, by what route, in what sequence, and why with that timing the ground becomes less firm again, the mystery remains not because nothing is known, but because so much is known in fragments. This is the strange position scientists often occupy at the edge of real understanding. The general architecture of the event is persuasive. The planet is deglaciating. Great ice sheets are melting. Fresh water accumulates in unstable proglacial systems. A circulation pattern crucial to northern warmth appears vulnerable. The North Atlantic cools abruptly. Sea ice expands. Feedbacks help sustain a cold interval lasting roughly 12 centuries. Then the system flips back. That story makes sense. It is supported by many lines of evidence. It is, in broad terms, the mainstream account. But the better this framework holds, the more visible its unresolved joints become. Take the freshwater trigger itself. The dominant view is that freshwater input plays a central role in weakening the Atlantic overturning circulation. But exactly which pulse of freshwater matters most remains debated. Lake Agassiz, or the wider glacial lake complex of central North America, has long occupied the center of the story. Yet the proposed drainage routes and dates have not remained as tidy as early versions once suggested. Some reconstructions support eastward drainage into the North Atlantic. Others imply northward release into Arctic pathways, or more complicated routing changes over time. Some geomorphic evidence once seen as decisive has become more contested. The core idea remains strong, but the map of the actual flood still flickers at the edges. Then there is the question of timing. Did the freshwater release come as one catastrophic outburst closely aligned with the onset of the Younger Dryas, or as a sequence of hydrological reorganizations that cumulatively destabilize the system? This matters because abrupt outcomes do not always require abrupt triggers. A climate system can absorb pressure gradually, and then cross a threshold quickly. If that is what happened, the search for one giant flood at the exact right moment may itself be too narrow. Scholars still debate whether the onset requires a single dramatic forcing, or whether background instability, meltwater routing, sea ice changes, and atmospheric feedbacks together create a climate primed to tip. The evidence remains incomplete because the geological record is better at revealing outcome than sequence. Sequence is the hardest part of all. Greenland ice may show abrupt cooling very clearly, but marine sediments, lake records, and terrestrial chronologies do not always line up at the same temporal resolution. Some archives respond to annual or near-annual conditions. Others average years or decades together. Some record temperature most strongly. Others record rainfall or vegetation. Radiocarbon dating, though powerful, comes with calibration complexities and site-specific uncertainties. Layer counting in ice is precise, but only within the archive it measures directly. The moment researchers try to align ice, mud, carbonate, charcoal, pollen, and shell across continents, they run into a fundamental problem: ancient time is preserved unevenly. This is why arguments about causation continue. If one region changes slightly before another, the causal chain may look different than if all shift in perfect synchrony. No single explanation fully accounts for every observed feature. That phrase matters here more than almost anywhere else in the story. Freshwater forcing explains much, but not every anomaly. Sea ice feedbacks explain persistence, but not necessarily initial trigger. Atmospheric reorganization explains wide-ranging consequences, but depends on something earlier in the chain. The impact hypothesis explains abruptness in a way that appeals emotionally, but not convincingly enough scientifically. A few researchers continue exploring volcanic contributions, solar variability, or more complex internal oscillations, but these remain secondary or supplementary rather than leading explanations. The Younger Dryas endures as a scientific problem precisely because it sits at the intersection of several powerful mechanisms rather than submitting cleanly to one. This does not mean all explanations are equally strong. They are not. The comet hypothesis, for all its public appeal, remains outside mainstream acceptance because the evidentiary case is too inconsistent. The missing crater problem, the disputed boundary markers, the weak reproducibility of some findings, and the absence of a widely accepted global impact signature all leave it on uncertain ground. It survives because it is dramatic and because a handful of anomalies remain intriguing, not because it currently explains the event better than ocean circulation models do. Scientific uncertainty should never be mistaken for equal validity of all ideas. Scholars still debate within a hierarchy of evidence, and in that hierarchy, freshwater forcing remains far ahead. Yet even within the freshwater framework, there is room for real disagreement. Some models suggest that the Atlantic overturning circulation may have weakened substantially, but not collapsed entirely. Others indicate stronger reorganizations under specific conditions. Some researchers emphasize fresh water entering the Labrador Sea or Nordic seas as especially important. Others point towards sea ice as the crucial mediator that translates modest freshwater changes into major atmospheric consequences. There are debates about whether background glacial warming makes the system more or less sensitive to perturbation at that particular moment. There are debates about how much of the Younger Dryas is best understood as North Atlantic-centered versus broader hemispheric rebalancing. And there are debates about the event's global reach, especially in the tropics and southern hemisphere, where the signals are real but often more complicated than textbook summaries imply. One lesser-known area of uncertainty involves seasonality. Many records tell scientists that climate changed, but not always exactly how the seasons changed. Did winters intensify more than summers weakened? Did growing seasons shorten mainly because of later spring melt, cooler summers, or earlier autumn frost? Did some regions become more climatically variable year to year, even if average conditions changed only modestly? These questions matter enormously for understanding biological and human consequences. A population can survive colder annual averages if summer forage remains reliable. It may fail under smaller average change if spring timing becomes chaotic. The same is true for human subsistence systems. Seasonality is often where climate becomes livelihood, but it is also where the ancient record becomes hardest to read cleanly. There is also the broader puzzle of why this event matters so much at precisely this point in Earth history. Deglaciation includes other fluctuations and abrupt changes, some dramatic in their own right. Why does the Younger Dryas stand out so sharply? Part of the answer is simply the quality of the evidence. Greenland ice preserves this interval extraordinarily well. Part is the event's timing, right at the threshold of the Holocene and close to major ecological and human transitions. But part may also be that the Younger Dryas reveals a climate system caught in a rare and unstable moment, neither fully glacial nor fully interglacial, sensitive to disturbances that would behave differently under other conditions. It is not just a cold event, it is a vulnerability event. In that sense, the enduring mystery is not a failure of science. It is a reflection of the complexity of the world being studied. The atmosphere, oceans, cryosphere, biosphere, and hydrological system are not arranged to produce explanations convenient for later minds. They interact in layered, non-linear ways. The Younger Dryas is one of those rare cases where scientists can see the interaction clearly enough to know that it happened, but not cleanly enough to reduce it to a single sentence without remainder. That is not weakness, it is honesty. Some of the most important truths in Earth history come with unresolved margins, and perhaps that is fitting. The Younger Dryas itself is an event of margins, the margin between Ice Age and Holocene, between mobile hunter-forager worlds and the first more rooted communities, between megafaunal abundance and extinction, between climatic instability and the relative calm that later civilization will treat as normal. To ask for a perfectly tidy answer may be to misunderstand the kind of moment this is. Transitional worlds are rarely tidy while they are happening. They only look neat from a great distance, and even then mostly in hindsight. Still, the mystery narrows. Scientists know far more now than they did a generation ago. New dating methods, better climate models, ancient DNA, refined sediment analyses, and improved proxy interpretation continue reducing the space of plausible explanations. The impact theory, once loudly promoted in popular culture, occupies a smaller scientific position than it did at its height. Freshwater and circulation explanations have grown stronger, even as their details remain debated. The bigger picture now looks less like an unsolved riddle in the dark and more like a landscape seen through fog, its outlines recognizable, its smaller forms still uncertain. What that leaves behind is a scientifically satisfying kind of incompleteness. The Younger Dryas is no longer mysterious because it might have been anything. It is mysterious because it was something very specific and very complicated, and the last steps toward understanding it require extraordinary care. A world of collapsing ice margins, unstable lakes, drifting sea ice, altered winds, and sensitive ocean circulation does not yield its secrets quickly. And in the end, that may be one of the event's most enduring lessons. The great changes that shape human history do not always come with a clean cause, neatly labelled at the bottom of the archive. Sometimes they survive as convergences, probabilities, feedbacks, and arguments that sharpen over time without disappearing entirely. The Younger Dryas remains one of those arguments, a climatic reversal whose broad meaning is clear even while its final trigger sequence still invites debate. By the time that debate enters the present, another truth becomes unavoidable. Human civilization grows up afterward in a climate calm enough to permit planning, farming, storage, cities, roads, states, writing, and all the deep assumptions of permanence that come with them. The Younger Dryas sits just behind that inheritance like a buried warning. It belongs to the world before settled history, but it is also the last great reminder of how fragile the calm to come will be. What follows the Younger Dryas is not merely warmer weather, it is the fragile calm in which nearly everything later humans call history becomes possible. Once the abrupt cold ends and the Holocene begins, the planet does not turn motionless or perfectly safe. Floods still come, droughts still return, rivers shift, volcanoes erupt, coastlines continue changing, and local climates fluctuate. But compared with the unstable closing millennia of the Pleistocene, the New Age is astonishingly steady. Seasons become more predictable, temperature swings moderate, ecological zones settle into patterns that, while never fixed forever, remain stable enough across generations to reward long-term planning. That stability is so foundational that later civilizations rarely notice it. They inherit it as though it were the natural state of the world. This inheritance may be one of the most important invisible conditions in human existence. Agriculture depends not only on seeds, tools, labor, and knowledge, but on the expectation that seasons will return in approximately recognizable form. Storage matters most when harvest can be anticipated. Villages make sense when local productivity can support repeated occupation without constant relocation. Herding depends on grass, water, and migratory timing that are variable but legible. States depend on surplus. Surplus depends on predictable ecology. Written records, taxation, monumental building, roads, armies, and urban specialization all stand eventually on this quieter foundation, a climate calm enough to allow deferred effort. The Younger Dryas ends, and in its wake comes the possibility of believing in permanence. That possibility begins modestly. In Southwest Asia, cultivation intensifies and village life strengthens in the millennia after the Younger Dryas. In different ways and on different timelines elsewhere, human communities begin transforming landscapes more deeply, whether through farming, burning, fishing intensification, monument building, or long-term settlement. Forests spread across much of Europe under early Holocene warmth, and people adjust to a world less open than the one their late Pleistocene ancestors had known. In the Americas, groups continue adapting to post-glacial environments, growing more regionally specialized as coastlines stabilize and the great ice sheets shrink away. Across many parts of the world, the old highly mobile Ice Age mode of life does not disappear at once, nor should it be imagined as somehow lesser. But the range of available futures broadens because the background climate ceases lurching between radically different states. This is why the Younger Dryas casts such a long shadow even after it is gone. It is not simply one cold event among many. It is the last major interruption before the long climatic corridor in which civilization develops. To understand that is to understand something uncomfortable about the historical world people usually take for granted. Cities are not just the product of human genius. They are the product of human genius operating inside unusually favorable conditions. So are kingdoms. So are libraries, canals, grain taxes, walls, laws, fleets, and empires. The calmer Holocene does not create these things automatically, but it stops slamming the door on them every few centuries with terminal Pleistocene violence. The difference is immense. There is a temptation to imagine stability as strength, but stability can also create forgetfulness. The longer a calm interval lasts, the easier it becomes to mistake it for permanence rather than luck. Communities build myths of order, states build calendars, farmers trust seasons enough to plant on faith, engineers divert rivers, raise ports, terrace hillsides, and shape entire landscapes under the assumption that nature is variable but broadly negotiable. Even when civilizations collapse, as many later do, they usually collapse within the same overall Holocene envelope that made them possible in the first place. They fall because of drought, flood, war, politics, disease, inequality, soil exhaustion, or combinations of these. But they still fall inside a climate regime far gentler than the one that had governed the end of the Ice Age. The Younger Dryas remains buried underneath all of that as an older memory the written world never directly knew. One lesser-known irony is that the very success of human civilization may depend on climatic predictability, to such an extent that people come to underestimate abrupt change precisely because they have not lived through enough of it. A forager in the terminal Pleistocene inhabits instability as a normal fact of life. A kingdom in the Holocene can come to think of its grain yields, river cycles, and coastlines as rights rather than conditions. The longer the calm lasts, the more natural it feels. This may be one reason modern people find the Younger Dryas so disquieting. It reveals that the world beneath civilization is not inherently stable. It only has been, by geological standards, for a remarkably fortunate span. The legacy of the Younger Dryas is therefore double. On one level, it is a memory of strain, a cold interval that tests ecosystems, pressures human communities, fragments megafaunal worlds, and delays the full opening of the Holocene. On another level, it is a threshold marker. It stands at the end of the old unstable order and just before the new stable one. It is the last time Earth, in the broad northern record, so dramatically reminds its human inhabitants that warming can reverse, that seas and winds and ice can conspire to redraw the map of the possible. After it, the new world does not become simple, but it becomes calm enough to build upon. That calm should not be romanticized too heavily. Early Holocene forests close over once open hunting grounds. Some old prey disappear. Rising seas continue drowning coastal plains that late Pleistocene people had used for generations. Human groups must still adapt constantly. The shift into the Holocene is not a gift handed down without cost. It is a trade. The open, dry mammoth landscapes fade. Large Ice Age animals vanish. Coastal territories are lost. New diseases and ecological challenges emerge in warmer, wetter settings. Yet for human societies capable of experimenting, storing, planting, and settling, the trade proves transformative. A world less dramatic is, in many ways, a world more buildable. This is perhaps the deepest answer to the mystery posed at the beginning. Why does the Younger Dryas matter so much? Not simply because it is strange, though it is. Not simply because scientists still debate its exact cause, though they do. It matters because it is the last moment before the world people think of as historical becomes climatically possible. It is the final hard hesitation before the long warming stability in which memory, agriculture, and settlement begin thickening into civilization. It is the frost shadow behind the first villages. And it also matters because it reveals how contingent that inheritance is. Human beings did not step into a guaranteed future. They stepped into a fortunate climatic interval that could easily have been otherwise. If the Younger Dryas had lasted much longer, if abrupt instability had continued to interrupt glaciation more severely, if the Holocene had arrived later or less steadily, the pathways toward cultivation, surplus, and large settled populations might have been delayed, reshaped, or regionally blocked. This cannot be proven in any direct alternate history, but the logic is difficult to ignore. Civilization is not merely a social achievement, it is a climatic opportunity seized. That realization narrows the distance between prehistory and the present. The same species that once endured the Younger Dryas now lives in cities of glass and concrete, under electric light, with satellites overhead and data centers pulsing through the night. Yet beneath all this complexity, the old dependency remains. Food still depends on rainfall, soil, seasonality, and circulation. Ports still depend on sea level. Entire nations still depend on predictable climate patterns they did not create. The old fragility has not disappeared. It has only been covered with infrastructure dense enough to hide it from casual view. So the Younger Dryas becomes, in the end, more than a story about cold. It is a story about how easily thresholds can be crossed, how deeply human lives are bound to systems larger than themselves, and how much of what later seems permanent is built atop conditions that once changed with startling speed. 12,800 years ago, the world seemed to freeze again for reasons not yet fully settled in science. A little later, it warmed again and held long enough for villages, kingdoms, and eventually nations to emerge. Between these two facts lies one of the most important and least visible dramas in the human past. The calm we inherited was never guaranteed. It was arrived at. It followed instability. It followed extinction, adaptation, migration, hesitation, and a climate system that had not yet decided to be kind. That is why the Younger Dryas still matters. It reminds us that the world which allowed civilization to grow is not the default world. It is the one that came after the freeze. The wind down begins where the ice once did, in silence too large for any one life to measure, long before cities, before kings, before grain fields and ports and borders. The earth is already capable of changing its mind. It warms, it freezes again. It opens a path and then narrows it. Mammoths move across ground that will not remain theirs. People follow rivers and herds through landscapes that will sink beneath the sea or vanish under forest. A flower leaves its pollen in the mud, and thousands of years later that tiny trace becomes the name for an age of sudden cold. What makes the Younger Dryas linger in the imagination is not only its mystery, but its nearness to everything that comes after. It sits just behind the settled world like a final dark threshold. On one side lies the unstable closing of the Ice Age, full of moving ice, drowned plains, great animals fading from the earth, and human communities forced to live by sharp attention to every season. On the other side lies the long calmer interval in which fields are planted. Villages return to the same ground year after year, and memory begins to accumulate in walls, roads, records, and ruins. Between them is this strange cold pause, this last hard reminder that the planet's generosity is conditional. The people who survive it do not know they are surviving a hinge in history. They only know the world has grown harsher, then kinder again. They know where the water is, where the wind cuts hardest, where the animals have gone, which plants still return, and which places can still hold a camp, a house, a future. That is enough. History often begins that way, not with grand awareness, but with endurance. And so the Younger Dryas remains in the earth, not as a legend, but as a layer, in ice, in dust, in lake mud, in the absence of animals that once seemed permanent. In the first more rooted human lives that emerge after the cold releases its grip, it is still there under the world people know now, under farms, roads, towers, harbours, and electric light. A buried memory of how quickly conditions can change, and how much of civilization rests on a rare interval of climatic peace. Perhaps that is the final image to hold on to, not disaster and not triumph, but a landscape in the first warmer centuries after the freeze, snow retreating from a valley, water running freer, birch and pine beginning to edge forward, human tracks returning to ground that had been too hard for too long, the old world not yet gone, the new one not yet fully formed, and everything balanced for a moment in the fragile calm that makes history possible. This speed is one of the most unnerving features of the entire episode. In Greenland ice cores, the onset of Younger Dryas conditions appears astonishingly abrupt. Exact estimates differ depending on which record, proxy, and calibration method is used, and scientists are careful not to overstate precision where the evidence remains incomplete. But the larger picture is clear. The shift is not spread lazily across millennia. It happens on the timescale of human lives. In some reconstructions, Greenland cools by several degrees in just a few decades. In paleoclimatic terms, that is almost violent. It means a child born into one climate regime could grow old in another, with no guarantee that the rhythms learned in youth would still hold by maturity. The cooling is strongest and most clearly expressed in the North Atlantic region, but it does not stay politely confined there. Europe feels it in changing vegetation, renewed periglacial conditions in some areas, and altered moisture regimes. In parts of the British Isles and continental Europe, open, cold-adapted plant communities expand again. Tree lines retreat or stall. Pollen records show a return of tundra-like signals where woodland had begun to spread. In lake sediments, the biological indicators shift accordingly. Aquatic life changes. Erosion patterns alter. Sometimes the most persuasive evidence is indirect, not the cold itself, but the ecological retreat that follows it. A forest does not argue. It simply fails to advance. In Greenland, the isotopic evidence is especially dramatic because the ice records temperature so finely. Ratios of oxygen isotopes in each annual layer reflect the conditions under which snow formed. As those ratios change, they reveal an atmosphere turning colder with startling speed. Dust concentrations also increase during colder, drier periods, suggesting changes in wind strength, source regions, and the amount of exposed sediment available to be lifted into the air. The Younger Dryas is not just colder in these records, it is often dustier, harsher, more like a climate system shifting into a drier and more abrasive mode. That combination matters, because it hints that the event is not a simple thermostat turning down uniformly. Atmospheric circulation is changing too. The name of the interval comes back here with quiet precision: Dryas octopetala, the small Arctic alpine flower that gives the Younger Dryas its name, appears in greater abundance in the pollen record because colder conditions once again favour the kinds of habitats in which it thrives. It is easy to miss how elegant and severe that is. A flower becomes evidence that a continent has slipped backward. Layers of mud, accumulating year by year at the bottom of ancient lakes, preserve the proof that warmth retreated and cold-adapted vegetation reclaimed ground. The record is microscopic, but the event it describes is continental. Yet even at its most severe, the cooling is not identical everywhere. This is where the event becomes more subtle than popular summaries allow. Northern Europe and the North Atlantic show some of the clearest and most dramatic signals, but other regions respond with different mixtures of temperature change, moisture change, and seasonal instability. In some places the main story is colder winters. In others it may be reduced summer warmth, altered precipitation, or the shifting boundary between grassland and woodland. Southwest Asia experiences cooler and drier conditions in many reconstructions, though the exact local expression varies. In some tropical and subtropical regions, changes in rainfall belts and monsoon systems may matter more than raw temperature. Scholars still debate how synchronous every regional signal truly is, and how directly they can all be tied to the same mechanisms, but the broad pattern remains undeniable. The Northern Hemisphere, especially around the North Atlantic, enters a renewed cold phase that interrupts deglaciation. Part of what makes this interruption so striking is that it does not fully restore the last glacial maximum. The vast ice sheets do not instantly return to their greatest extent. Sea levels do not rewind to where they had been thousands of years earlier. The world does not become a perfect copy of the old ice age. Instead, it re-enters something closer to near-glacial conditions in many northern regions. The cooling is severe enough to reverse vegetation trends, strengthen winter conditions, and prolong the survival of cold-adapted landscapes. but it takes place in a world already transformed by substantial melt. This gives the Younger Dryas its peculiar atmosphere. It is not the old frozen world restored exactly as it was. It is a colder, harsher interruption inside a world that has already begun to thaw. That distinction matters for everything living through it. Plants that had begun advancing are checked. Animals exploiting newly productive mosaics of wetland, shrubland, and early woodland face disrupted food availability and altered migration patterns. Human groups adjusting to warmer conditions now encounter a world turning unreliable again. A route that had become passable for more of the year may once more become difficult. A stand of useful plants may shrink. Water sources may freeze longer or dry differently under altered seasonal regimes. The event is sudden enough to be experienced not as abstract climate, but as practical instability. It changes what a year feels like. One of the lesser-known aspects of the onset is that the cold does not simply fall from the sky in isolation. It appears bound up with the behavior of the ocean, sea ice, and atmosphere together. In the North Atlantic, a reduction in the overturning circulation would mean less heat transported northward. If that happens, sea ice can expand. Expanded sea ice reflects more sunlight, reinforcing cooling. Atmospheric pressure systems and wind tracks adjust in response. Storm paths can shift. Moisture delivery changes. Snow cover persists longer, increasing surface reflectivity over land as well. The cold becomes self-supporting, at least for a time. This is one reason abrupt changes are so feared in climate science. Once a threshold is crossed, feedbacks can help hold the new state in place. And hold it in place they do. The Younger Dryas is not a brief cold snap. It lasts roughly 1,200 years. That number needs to be felt properly. This is not a crisis passing in 3 generations. It is long enough to become the normal world for dozens of generations. A child born at its onset dies in a cold world. So do their grandchildren and their grandchildren's grandchildren. Memory of the earlier warming can survive only as inherited knowledge shaped by movement, practice, and story. If it survives at all, communities adapt because they must. Ecosystems reorganize because they have no alternative. The cold is sudden in onset, but then it stays. That staying may be as consequential as the speed with which it begins. Still, the onset remains the central puzzle because it is where causation must be sought. Something tips the climate system out of its warming trajectory and into renewed cold. Scientists return to this moment again and again because the records are rich enough to show the change, but not always rich enough to explain it cleanly. In Greenland, the transition is crisp. In ocean sediments, the changes in currents and temperatures are recorded through shifting microfossils and geochemistry. In lakes, pollen and organic remains capture the ecological reversal. In cave deposits, isotopes hint at altered rainfall patterns. But linking these records into a single sequence of cause and effect is hard. Did freshwater flooding weaken ocean circulation first, with atmospheric changes following? Did sea ice expansion amplify an already disturbed system? Did regional effects begin at slightly different times, giving the illusion of simultaneity from one vantage and lag from another? No single explanation fully accounts for every detail of timing in every archive. The apparent rapidity of the onset has also made the Younger Dryas a natural magnet for dramatic theories. Sudden changes invite singular causes. Human imagination prefers impact, explosion, catastrophe from above. That instinct is understandable. When a climate shift seems to happen fast, it feels as though something equally dramatic must have struck the system. But the paleoclimate record often teaches a more uncomfortable lesson. Large systems can contain their own abruptness. They do not always need an external blow, a threshold crossed inside ocean circulation, freshwater balance, or sea ice extent can produce consequences that feel catastrophic without any comet at all. The climate system is perfectly capable of surprising the creatures living inside it. Even so, the event's speed remains shocking enough that it resists domestication. Modern people are used to thinking in centuries when discussing climate. The Younger Dryas refuses that comfort. It reminds us that change can happen on the scale of experience, not just history. A landscape can stop becoming more hospitable and start becoming harsher within the span of ordinary lives. The transition from thaw to renewed cold can occur not as a mythic turning point visible to all, but as a succession of practical losses and altered expectations that accumulate year by year until the old world is plainly gone. Imagine northern grasslands growing less reliable under shorter summers. Imagine the edge of woodland halting and then retreating. Imagine stronger winter conditions holding lakes and rivers in cold longer than recent memory suggests they should. Imagine sea ice pushing farther, storms tracking differently, dust rising more often from exposed ground. In places the signal may be temperature, in others it may be dryness, or seasonality, or the collapse of ecological predictability itself. For the people and animals living through it, the effect is the same. The world stops opening and starts tightening. This tightening leaves a signature across multiple forms of evidence. Beetle assemblages in Europe indicate colder conditions. Lake levels shift in some regions as moisture balance changes. Lues, the fine wind-blown dust that accumulates under cold and dry conditions, becomes more active in certain landscapes. Glacial readvances occur in some mountain systems. In the eastern Mediterranean and Near East, botanical evidence suggests contractions in plant productivity and altered moisture availability that may have affected human subsistence. Not every site tells the same story in the same way, and scholars still debate local chronologies and causal chains, but the convergence is too strong to ignore. The cold is real, and it is widespread enough to matter profoundly. The warming world of the Burling Alarud had invited expansion, experimentation, and ecological rearrangement. The Younger Dryas onset interrupts all of that with remarkable speed. It does not erase the changes already underway, but it arrests them, redirects them, and in some cases punishes the very species and communities that had begun taking advantage of the thaw. This is why the event remains so compelling. It is not merely a cold interval in prehistory. It is a sudden reversal at the threshold of a new era. It is the moment when Earth, apparently on its way out of the Ice Age, seems to rethink its decision. And once that cold has arrived, the next question becomes unavoidable. How do scientists know all this so precisely from a world with no written record, no thermometers, no witnesses who can speak across the gap? The answer lies in places that preserve time differently in the ice of Greenland, in the mud at the bottom of old lakes, in ocean floors layered with microscopic remains, and in the hidden chemistry of stone. To understand how the Younger Dryas is reconstructed at all, it is necessary to follow the evidence itself,